All right. Good afternoon, everyone. Thank you for coming to the population level effect estimation applications to generate reliable real-world evidence. And we have me, George Hripcsak, Martijn Schuemie, Linying Zhang, and Tara Anand here to give the tutorial. And it's kind of a fun, interactive thing. So here's our description of the tutorial. We're doing population level effect estimation or causal inference. We're going to figure out how to say if you have an exposure to medical interventions, how are they expected to impact health outcomes? How can we estimate that in a fast, reliable manner? So that's what we'll be talking about today. Kind of using a multimodal approach today. Here's the schedule. I'll give a little bit of an intro on observational research, and then Linying will talk about causal inference. And Linying is going to give theoretical, not highly mathematical, but still a background kind of why we want to do it and what we want to do. Then we'll have an interactive section on study design by Martijn, a break. Then Tara will give more of the practical side of cohort method and diagnostics, how to really do it. Martijn will give the second half of that on meta-analysis and negative controls. And then we'll have a more interactive session. So remember, I had emailed around to the participants that if you wanted to, you could bring your laptop. If you installed our Studio and the Hades and Strategus code, then you could follow along during that last hour session, and we'll create a study. There's not enough time in a tutorial like this to actually run the study for an hour or 2 hours. So what we would do is start, because we have to give all the instruction before that. So we're going to, we have the opportunity to do, now first, if you haven't brought that, don't worry, we're going to follow along at the podium. But if you have brought it, you can design the study, get through the code, and if you have a database to get to, you can start executing and see if you get any runtime errors early on in the thing, and then run it later or continue to run it after the session has ended.
Maybe mention that I'm putting the slides online.
Oh yes, thank you, Martijn. So the slides will be on GitHub in a moment, and in case you want to follow along on that, although we're lucky because we have the big screen in this room, so you need it less than the other rooms which have a smaller screen. So OHDSI is succeeding in publication and impact. You know, we're now publishing in the world's top journals, Lancet, BMJ, JAMA. We're changing guidelines. The European hypertension guideline was altered by our evidence specifically. And we're affecting hundreds of millions of patients. The hypertension guideline is one example. Another is COVID-19 AstraZeneca vaccine got turned on by our data in 2021. But the field remains skeptical, and there's the gold standard of randomization in observational research. At least it's felt that it's subject to more contradiction, highly biased, publication bias. And so it's not trusted to the extent that journals won't publish studies that have causal assertions in them, even though, of course, a whole point of publishing a study is to assert causation, even if it's imperfect. We're not allowed to use that language because it's observational research. So our goal is to say, how does OHDSI address this skepticism? What are we doing? OHDSI has created, I think, an incredible platform for efficient creation of reliable evidence. So we'll give an introduction to that platform, what it aims to do and how to use it. And then it complements other sources of information about OHDSI, like the Book of OHDSI, Eden Academy, and the summer schools. So when we talk about reliable evidence, there's a set of words up there that, this is Patrick Ryan's slide, repeatable, reproducible, replicable, generalizable, robust, calibrated. You can define those words in different ways. But bottom line is, if we switch the researcher, if we switch the database, if we vary the hypothesis slightly, as we change things, do we get the same answer? And that's what we are want to achieve, is that we get either the same, if we're supposed to, or a similar answer. How does OHDSI get there? Well, several years ago, Martijn Schuemie published an article in JAMA outlining 10 procedures, 10 principles for how to achieve reliable evidence. And I won't, instead of reading them, I'm going to show you a figure that I abstracted from that. And basically, you can classify them into two halves, verified and open. On open, we want to have a fully specified public protocol for our study, so we can't cheat on it later on when we don't get the answer we don't like. All our studies, all our software is open source so that with public parameters so people can repeat our experiment. We share all our diagnostics. Even before we see our study results, other people see our diagnostics to see that we passed. Then we share all our study results, so less subject to publication bias. And we enumerate where we ran the thing, like the characteristics of the databases we used. On verified, we use previously verified methods that address confounding. We have extensive diagnostics. These are things we're going to spend some time in this tutorial. We test many hypotheses at once to assess operating characteristics, not the one just the one we're interested in, but several around it. And we study on many databases. And in fact, tomorrow's plenary session is largely about that last item I just mentioned. So I'm going to go through stepwise on the next slide. But on this slide, you see that we worry about the data quality. Then we do phenotyping, which I'll define in a little bit. Then we do the analysis and we share it. And this tutorial is mainly about the analytic side on causal inference. So we write a protocol, right? We said we pre-specify the protocol. Why? Because we don't want to be able to change it when, as I said, we don't get the answer that we want. And it, you know, people don't sometimes do these things on purpose, but you inadvertently end up cheating. You add one more variable to the answer, you're like, well, I think I really did need that variable. You review your protocol before you run it, you curate the data, select cohorts, implement the analysis, and then eventually disseminate the evidence. And then you want to know, did I do a good job? So at the design level, we can worry about, well, do we use proper methods? Are they biased? Is there measurement error in our cohort definitions? How's our data quality in the database? If we get all that right, then our study design should lead to unbiased effect estimates, or relatively so. In addition, once I have the design, do I execute it properly? So is my programming correct? Is my logic correct? Is my ETL that I converted my data over to correct? These are the technical concerns which answer the question, does my analytic package do what my design said it was going to do? So this is where we want to get, these are the steps we want to achieve. Now why? I can relate what OHDSI does to kind of a classic validity framework, and I'll just do that in a couple of slides. Why would you get an answer that differs from the truth? Well, first of all, there's random variation, right, depending on your sample size. So you're going to get an answer differs from the truth just because it's too small and you have a wide confidence interval. Second reason is you may have errors in measurement or analytics. Are you really measuring the thing you want to measure? Those differences in approach are an example. And third, there may be real differences. You may be studying an older population in the Medicare database, and you have a different database that has only people under 65 or only pediatrics, and you'll get a different answer for, say, heart attack, myocardial infarction rates. So the population differs. And so there's random error, systematic error, and then at the top, what's also a form of systematic error, I'll call it diversity, that we want to see some diversity in the population so I can generalize it. So there's the study population of your actual subjects that went into your equations. And then through statistical inference, we draw conclusions about the population that you sampled, who you were drawing from when you created that sample. Then that's different from the target population, the people you were hoping to sample. So you say in your paper, I was doing this, but it turns out I was doing that, and that's difference. It leads to errors in causal inference, for example. And then finally, there's the external population that you want to draw conclusions about. That is the people I want to make medical decisions in. That's the external validity. So we have statistical inference where we find whether there's an association, internal validity, where are the conclusions valid within the setting of the study, and then external validity or generalizability, can the conclusions be applied to other settings, other patients? So for statistical inference, you know, it's things like type 1 and type 2 errors. Is my p-value correct? So that's association. What does OHDSI do to improve this situation? It does large network studies to increase the sample size, and it does proper statistical inference. Internal validity, a lot of our time today is going to be spent on this one. So that's the extent to which a study is free from design biases that threaten the interpretation of the results. Do you have a causal relationship? So for that, we do proper study design, confounding control, diagnostics, and network studies. And then external validity, generalizability, does it apply to others? And what OHDSI does is large network studies to get a more diverse population. On top of that, we can do heterogeneous treatment effect within our population, within a database. You can look at young and old, male and female, and so on. But having a large network allows us to generalize to other populations. So OHDSI seeks to generate evidence in 3 ways: what, why, and who. What is clinical characterization? Like, who takes metformin? Just tell me who takes the drug. The why, population level estimation. Does metformin cause lactic acidosis? Why did I get lactic acidosis? Was it due to the metformin? And who, given everything you know about me or your patient, is that person likely to get lactic acidosis? And we're going to focus on the middle one today. So let's talk about population level estimation. Does intervention A cause outcome Y? Does a drug cause a side effect? So first you have to ask, compared to what? So is it compared to another intervention, B, or compared to not giving A at all? If we were to study hypertension today, would I do comparing a drug to not getting a drug at all? Can I do that study? I can't do that study anymore because it would not be moral, because we know that not treating hypertension would lead to higher heart attack rates. So we have to compare it to another alternative treatment and see if it's better or equal. So a lot of the work we do is these comparing 2 cohorts. So it's a comparative cohort design, and that's where we're going to spend a lot of our time this afternoon. We can still study. Now, in some cases, comparing A to not A, should I vaccinate or not, in certain cases may make sense. There, we can use different designs like a self-controlled case series. We will touch on that during the 4 hours, but we're not going to go into deep detail on self-controlled case series. But a lot of the concepts are common between the two, a lot of the diagnostics and so on. So new user, that is the first time I'm using a drug, cohort design comparing 2 drugs is shown graphically here. I have my total population that I started with, and then I divide it into 2 groups, some in the target cohort and some comparator group, say another drug. And then I follow their longitudinal record, the arrows on the right, and I look to see if they get an outcome, which could be a bad effect, signified by the yellow circles. And so the question is the outcome or any difference in the outcomes due to the difference in the drugs? In order to assert that, I'd like the 2 groups to be equivalent in all ways except for the drugs. So if I am doing a randomized controlled clinical trial, I use I take one group, randomly divide it into 2. Now I know those 2 groups are equivalent. I give one drug to one. I give a different drug to the other. I blind it so you don't know which drug you got, and I check the outcomes for a difference. What we're doing here is observational research. So for example, if one drug is known to be safe or thought to be safer, better for sicker people, the doctor may give that drug to sicker people. Then when you check the outcomes, they may get more outcomes because they were sicker to begin with, not because the drug was different. So the belief of the doctor affects the groups, which then affects the outcomes beyond the effect of the drug. So what do? And we'll be explaining different ways that we do this. We adjust the groups, or we adjust the analysis so the 2 groups become comparable. And Linying will go over that in the next talk. And then actually the whole theme will be that. Now for our interactive sessions, we picked an example that we can use. So we'll exploit our experience in hypertension treatment, which has had, as I said earlier, a huge worldwide impact. We're going to compare angiotensin-converting enzyme inhibitor drugs, ACE inhibitors, to angiotensin receptor blockers, or ARBs. They're thought to be interchangeable on effectiveness. So when you take a hypertension drug, your hope is to reduce the rate of people having heart attacks and strokes later on. People point out that only ACE inhibitors have had placebo-controlled trials for that very reason I mentioned earlier. ACE inhibitors were invented long enough ago that we didn't have proof that treating hypertension works, so we were able to compare ACE to nothing. Now we don't do that anymore, so ARBs have never been compared to placebos. ARBs are thought to be safer, especially on things like cough and angioedema. Angioedema being a dangerous swelling of the skin. They both affect the renin-angiotensin-aldosterone system. One blocks the creation of angiotensin II, the other blocks the binding of it, but they both relax blood vessels and lower blood pressure. So we'll compare those two treatments for essential hypertension, looking at effectiveness in the form of acute myocardial infarction or heart attack, and safety in the form of angioedema, as I mentioned. And there's actually one of our studies, ACE versus ARBS, which was picked up in JAMA News, and then an editorial was written about it in Circulation, which said it's time to change the guideline. The US guideline hasn't come out again since then, so we'll see if they change the guideline in response to that paper. Good. So we're going to be talking about analytics mostly in these 4 hours. But when you actually do a study, you find that often like a lot of your mistakes occur in an earlier stage. And we didn't want to go without mentioning the OHDSI tools for helping you do one step earlier in the process, or phenotyping, which I'll talk about in a moment. So I showed you that previous diagram, and I drew my red circle further down. My red oval is now up at the phenotyping stage. So I'm going to just spend a little bit of time as part of the intro talking about OHDSI's tools for phenotyping, so you don't go into it without any background in that. Although we do have other years we have an entire tutorial on phenotyping. So the first step is common data models. So you have databases along the left, which are in different formats, and we reformat to the same common data model in the middle and the same vocabulary, and that way we can design an analysis, write the code, and run it across all these databases without individual tweaking. Then we do the phenotype. So what is a phenotype? It's a specification of an observable, potentially changing state of an organism. And it can be applied to EHRs, where our goal is to learn about some clinical concept we care about. Do they have diabetes? Did they take the drug ARBs? Based on EHR data or claims data or other clinically relevant data. So OHDSI tends to use the word cohort. What's the difference? Well, a cohort is an example of a phenotype, I guess. The important thing about a cohort in OHDSI is time. Often when you talk about phenotyping in the field of informatics, it's a classification task where you just want to figure out, did the person ever have a heart attack or not in the past? With OHDSI, the thing is I need to know when they had the heart attack, when did the condition stop, and when did it end. So a cohort is a set of persons who satisfy one or more inclusion criteria for some duration of time. And the cohort definition is a specification how to identify the cohort. So why is this a hard thing to do? I want to know who has a heart attack. I've got a vocabulary. I look up myocardial infarction in the vocabulary. It says it's an OMOP code 4329847. Aren't I done? I just found out everyone who's had a heart attack. And so, well, that doesn't work so well. And here's an example and when I teach the medical students, I say, tell me what PERLA means. Can anyone tell me what PERLA means? So they say pupils equal, round, reactive to light, and accommodation, because they're medical students and they just learn this. And then I say to them, I didn't ask you what it stood for, I asked you what it means. And those who have been on in clinical care for a little bit get the joke and start laughing. Because what it means is you looked in the direction of the patient, they appeared to have two eyes, and I wrote down PERLA in my chart. But I didn't no one checks for reactive to light and accommodation unless you're a neurologist or an ophthalmologist. And even my ophthalmologist never checks for accommodation. So, there's what the word supposedly, what the word says, that is what it stands for, versus what it's written in the record. You could actually do a study. So the picture is a woman with one eye, one prosthetic eye. So she can't be PERLA because has only one pupil. It can't be equal. And so 2% of people with one eye are PERLA in their exam. So it means they certainly didn't check. And then another 8% of people are PERLA on the left or PERLA on the right. I know what they mean, but you can't actually be PERLA on the right because you can't be equal on one side. So what they mean is, and these are ophthalmology notes, what they mean is they're equal and round and maybe reactive to light. I mean, not equal, but round and reactive to light and accommodation. In our case, myocardial infarction, they write myocardial infarction, but what they may mean is rule out myocardial infarction. So when you're writing in the chart and you want to order a test and you want to get paid for it, you have to say why you did the test. And what you say is MI. But they didn't have an MI. You're checking if they had an MI. So what you mean is rule out MI. But what they write down is MI. So if you do a trivial study and you build a cohort based on people who have an MI code, you're going to get people who don't have an MI and are proven not to have an MI, in fact. A lot of the data are missing. The data are clustered. The chart on the left is either those are admissions or when the patient was sick. The chart on the right is a single point. Someone came into our emergency department, had a hurt finger, and went home. You can't do a lot of research on that person. So you need to accommodate these different properties of what's in the chart. And then it's often inaccurate. Now, this is from 1997, 50% accuracy. Now, that was like the low end, which was for smoking. Is this a smoker? That was 50% accurate. For things like diabetes, it was closer to 90% accurate, so it's more, but still it's not 100% accurate. So the purpose of a phenotype or cohort definition is to accommodate failings or properties, because they're not necessarily failings. I see them as, it's better to see them as properties of clinical data, not failings. Like, these are valuable data. One point I make to the medical students is doctors read these charts and do a pretty good job understanding what really happened to the patient, because they read it and they know. They see a perler, they know, all right, well, that doesn't mean very much. So they know how to interpret it, and that means our phenotype algorithms have to know how to interpret it. So we look for repeated codes. If you have a lot of MI codes, they probably really had an MI and not a rule-out MI. And we triangulate using alternative sources of information like drugs and labs and procedures. So what we have is a longitudinal record of different data types. What we want are phenotypes that start and end at something. The top one is type 2 diabetes, hyperlipidemia, and so on. That's what we want. But we make mistakes. Sometimes we get the timing wrong, and we want to know when they actually started with the disease, although that's a soft concept. And we have some false positives and false negatives, and we need to work around that. So we do that with the Odyssey pipeline, shown here, where we review prior work, we figure out what concepts we want to use, we then engineer the phenotype logic definition, and then we do diagnostics to see how well we did, and then if it works, we store it in the library. So I'm just going to go through that for a few slides, and that'll be the end of my section. So Atlas is Odyssey's tool that we use for phenotyping. It's available as atlas-demo.odyssey.org for you to use, and then sites tend to have a version of Atlas running on their own database. So I can go in there and type in myocardial infarction to see who's had a heart attack, and it'll tell me that code I showed you before, 4529 847 myocardial infarction. Then this vocabulary has a hierarchy, an ontology. So myocardial infarction is shown there, and underneath it are specific examples of myocardial infarction, like acute MI, and subendocardial MI, so specific examples. When I'm building a phenotype, I'll exploit the hierarchy. I generally take the most general code and pull along everything I need with it. If I find I want everything with it, but there's one I don't want to include, I can then exclude that one. And again, this is like a whole tutorial worth of phenotyping I won't go through, but there's the ability to do that. The other thing I point out is when you look at the hierarchy, you may look and say, hey, wait a minute, I was putting myocardial infarction. I don't want that. I want acute myocardial infarction. I want to know who's having one of those MIs right now, because that's going to be the start of my cohort. I don't want to know who's had one 10 years ago. So you have to make that decision when you're doing the knowledge engineering. Which of those two things do I want? And then you want assistance, maybe, because not everything is in the hierarchy. The hierarchy is never going to be perfect. So Anna Astrodopoulos put together a tool where she asked everyone in the world, how often does every clinical concept happen in your medical center? And about 30 people answered from around the world, creating a knowledge base from which we could say, given any code, pre-compute for every code, 11 million concepts, well, 3 million standard ones, what's every other concept related to it? Either because it has the same name, myocardial infarction appears in the term, or because it's related in the hierarchy as a sibling, or because they occur together in the database. And then she created this user interface in Atlas, which makes suggestions. And so here's an example for us. Cardiac rupture due to and following acute myocardial infarction. So this is a code that's not in that hierarchy. It's not underneath MI because it's not an MI. It's a cardiac rupture, which is a different thing. But it has MI in the name because it's due to it. If they had one of these codes, they must have had an MI in the past. So if you want to increase your sensitivity, you might include this code. And Phoebe points you to these kinds of codes that you can include. Then you have to build your logic, which is a triggering event that gets me into the cohort. What are my inclusion criteria to say that it's relevant? So my triggering event might be I start a drug, semaglutide. My inclusion criteria, I want to make sure I'm taking it because of diabetes, not obesity. And then I need exit criteria. What gets me out of the cohort? And then Atlas provides you with a semi-graphical, kind of a linearized and/or group. And in this case, I put the logic there. Like I could look for 2 myocardial infarction codes, so I don't get so many rule-out MIs instead of MIs. Then I evaluate the phenotype. First thing I do is just look at it. Run this phenotype definition on my database, look at the cohort. Does it have the properties I expect? Male versus female, young versus old, what year it happened. Then normally what you would do is a chart review if you want to be fully rigorous. Does the algorithm identify the cases accurately? But you can't check a 1 million person database by hand. If it finds a case, you can check that case and calculate positive predictive value. I won't go through this short thing and what that is, but if I want to find out if it got all the cases, there's no way to do that other than looking through 1 million cases. So that's hard to do. So what can we do to facilitate that? Well, one thing we do is provide Keeper, knowledge-enhanced electronic profile review system, also by Anand Sotopoulou, which uses summarized structured data to replace the chart review, which is twice as fast, increases consistency, and just as accurate as doing the chart review for the phenotypes that she studied. And the other thing we can do is Phevaluator, which uses machine learning on highly sensitive and highly specific alternative phenotypes. Like, let me just pick everyone who has 5 MI codes in their database as probably having the MI. Use that as highly specific, and one is highly sensitive, any evidence whatsoever. And then I train a machine learning algorithm, and then I estimate the sensitivity and specificity of your phenotype using that algorithm. So that's kind of a wacky thing. Like, it shouldn't necessarily work. But in fact, empirically find it comes up with pretty accurate estimates of sensitivity and specificity. So it's another tool available to you. And then finally, if I'm successful, I share that phenotype in the phenotype library. Okay, so I'm going to stop there. So any questions about phenotyping? Okay, so we just want to give that rapid thing, and now we're going to turn it over to get to the core of our tutorial on causal conclusions from observational data. So Linying.
Hello everyone, I'm Zhang. I'm assistant professor at WashU, and today I will be walking you through causal inference or population level effect estimation. I hope that phenotyping challenge didn't scare you away. There are many tools there to ensure that you can create perfect, near perfect phenotypes. So assume you have done that, and now you're ready for the analysis. You want to know if one drug is actually safer or more effective than the other. And that will be the focus of this part of the tutorial, is how can we draw causal conclusions from observational data. Here's my motivating example. I hope to motivate you. It is not hypertension. George has published almost every possible comparison of hypertension. It's no longer motivating to me. So I picked something else, type 2 diabetes. So currently GLP-1 receptor agonists, which is a class of anti-diabetic drugs that have been initially approved for treating diabetes by lowering blood glucose, but it has recently been we have seen more widespread use because they can also help reduce weight. Although all anti-diabetic drugs help reduce the risk of cardiovascular outcomes, it's yet not clear to us that whether the effect of GLP-1 has a bigger effect on lowering the risk of cardiovascular outcomes compared to other anti-diabetic drugs. So we're studying diabetes or comparing anti-diabetic drugs on some cardiovascular outcomes. Great. All right, so let's now more formally state what exactly is our research question. And here's what I propose. You're going to study with me today in this 45 minutes and also in the interactive session that's towards the end of the tutorial. So we want to know, do GLP-1 receptor agonists, or we just call it GLP-1s for short, reduce the risk of acute myocardial infarction more than DPP-4 inhibitors? There's a lot going on, so let me unpack this question a bit further. Questions like this can be summarized into this template. We're doing a comparison study. We're comparing risks of a health outcome between a target treatment and a comparator treatment during some time at risk. So can someone tell me, if you look at the question and this template, let's match the terms. What is the outcome that we're interested in here? Do I get any volunteers? Myocardial infarction. Can be more specific. Excellent. So the outcome we study is acute myocardial infarction. And can someone tell me what is the target and what is the comparator here? Can I get another volunteer? Maybe the table in the middle?
GLP-1, DPP-4.
Excellent. You got 2 points for answering both correctly. Yes, so the target is GLP-1s, the comparator is DPP-4s. I mean, if you switch that, that's okay, as long as you know which one is your target, which one is your comparator. And we study at some time at risk, as George mentioned. In our cohort studies, a cohort is not a simple classification algorithm, but we want to know at what period, right, what is the follow-up time. Sure. Okay, so you have already helped me identify what is the target, the comparator exposures, the outcome of interest. The time at risk, in the Odyssey network studies, PLE studies, there's sort of like 2 common ways of defining time at risk. One is called on treatment, the other is called intent to treat. I will begin with the intent to treat because it's simpler. So intent to treat means the risk window ends at the end of observation. Right? If you have an EHR database, if you observe a patient for 5 years, you identify when they start taking GLP-1s, and at the end of, so basically it's a once on, always on kind of approach, right? Once they start the treatment, you don't care what really happens afterwards. You treat the end of observation, like their last clinical encounter, as the end of your follow-up period. But you may go, well, this is not very, right? This doesn't work for me because the patient can switch treatments, or the patient can, do sort of all kinds of crazy things that it would make them you consider them no longer eligible in the target cohort. And in that case, that implies you want to adopt a more like own treatment design, meaning you want the risk window ends at treatment discontinuation. Let's say, right, in my target cohort, these patients started with GLP-1s, but later on, they switched to some other anti-diabetic drugs. And if you would, at that point, you would consider these patients no longer in your target cohort. So that'll be an own treatment design. Or these patients can be on GLP-1s, but there's a 1-year time gap between 2 prescriptions, and that 1 year makes you think, well, then, right, I don't know what happened to them during that 1 year, then I will treat the last prescription right before that 1 year gap as the end of my observation. And this is a very case by case, right? 1 year might be a very long time window for some drugs, but it may be okay for some other drugs. Similarly, a 10 days gap could be negligible for some drugs, but for others, it could be a big enough time gap. So these are always things that we discuss with clinicians in the team when we design network studies, and we specify this in the study protocol before we run any analysis. All right. So I'll elaborate a little bit more about this time at risk and the 2 common study designs we adopt. So, right, to recap, the task is that we now want to learn the causal effect of these drugs from observational data. I want to know if one is better than the other in reducing the risk of acute MI. All right, next Are you ready to go into a fantasy world with some time machines? Right? Let me take a step back. Observational data, real world data, it's always so messy. It gives me a lot of headache. And answering causal questions with that data is really hard. But now you don't have to live in that world for the next few slides. You're living in this fantasy world where you got to do some magic to estimate causal effects. And that magic you have is a time machine. So you can send people into the future, bring them back, and have a parallel universe that they can experience something totally different from this world. All right? So how's that going to help us with identifying causal effect? Right? We're interested in two drugs. Wouldn't that be ideal if every individual in my cohort can take one drug and for me to look at the outcome, and also I will send the exact same person to be on a different treatment and observe their outcome, right? I'll let the cartoon, I think it helps better explain what I mean. That's my cool time machine. All right, so what just happened on the slide is, right, this is my target cohort, these three little guys. I first sent them down the path of taking GLP-1 receptor agonists. I look at observe their outcome, and then I use a time machine to send these exact same people back to where, right before they started the GLP-1 treatment. And this time, I send them all to take the comparative drug, the DPP-4 inhibitors, and then I observe what happened to their health outcome when they're on this alternative drug. So what we can conclude, two things. One, I hope that this convince you this is the exact same three guys, same cohort. There's nothing different between them. The only difference is that the first time they got the red pill, the second time they got the blue pill. And then I observe the outcomes following each treatment. And you can probably conclude that here. When they take the red pill, one guy was unhappy, two were happy. When they took the blue pill, two were unhappy, one was vomiting, like really hated this drug, and one guy was okay. So my red pill probably works in this case. But there comes a but. We don't have that time machine or that magic. So what do we do in this world? If you have a pharmaceutical company develop a new drug, what do? Right? They don't have a time machine, but they produce some causal estimates. And that is through randomized controlled trials. Right? When a drug enters the phase 1, 2, 3, and then we get the causal estimates from a new drug. And how they do it, instead of using a time machine, is that they randomize the treatments. So they recruit a group of participants. They send half of them to take the red pill, half of them to take the blue pill. It's a totally randomized process, which means is that the people who got the red pill versus the blue pill, they're comparable, right? They're exchangeable at the baseline. There's no difference between them other than the treatment that they received. So in this case, when we review the outcome at the end of the study, any differences we see in the outcome between the two groups can not be attributed to anything but the difference in the treatment they got. So that is through randomization how the random RCTs establish causal conclusions or causal relationships. All right, that's cool. But still, right, not every one of us has $10 billion that to throw into an RCT trial. So what do? Right? We have this real world data that could be millions of patients, and it's a very valuable resource. You want to make use of it. Right? People are in the real world, when they see doctors, they take different treatments. We see their, some people experience acute MI, some don't. We should be able to infer some causal relationships from that data, even though the treatment there was not randomized, So the technique we use, or in biomedical research, the most popular one has been propensity score for the past several decades. I will go into propensity scores in more details in the next few slides, but this shows just using this very cool slides and the cartoon, right, to show what a propensity score is. It's a probability of getting the target treatment given patients' baseline characteristics. And if we do, for example, matching on propensity score, in this case, for example, right, this first green guy who got the red pill, his propensity score, his probability of getting a red pill based on his characteristics at the baseline is 70%. And this guy, this yellow guy, even though he got the blue pill in the data, but his probability of getting the red pill is 0.68, which is close enough to 0.7. So if we match on propensity score, meaning, right, if they have similar propensity scores, meaning we consider them to be comparable. And that is how essentially what propensity score does. So in observational data, observational studies, you probably have heard this phrase, association is not causation. And this happens a lot in observational data. So I want to use this intuitive example to explain what that means and what problems can cause if you do not account for this fact. So imagine if I want to study the risk of carrying lighters in pocket and the risk of lung cancer. I have an observational data, meaning I record who carry lighters in their pocket, what their smoking status, and whether they have lung cancer. You would find that in the population that carry lighters in the pocket, the incidence of lung cancer is much higher. Right? It looks as if carrying lighters causes a higher risk of lung cancer, but we all know that could not be true. But why do you see this association? It is likely that people who are smokers are more likely to carry lighters in their pocket. And in other words, right, smoking status changes the probability of whether they carry lighters or not. And also smoking, we know that it's a risk factor for lung cancer, right? It changes the baseline risk of lung cancer. So in this case, smoking status is a confounder. It affects who carry lighters around the treatment assignment, and also it affects the risk of the outcome. So what do we do in this case, right? Assuming smoking is the only confounder in our study, what could you do to de-bias this study?
So you patients who carry the lighter but don't smoke?
There are people who carry lighters but don't smoke.
Yeah,
We allow that happen.
So this is your target cohort in this case?
Yeah, but you will lose a lot of samples in that way, right? Because most people are probably, there's a higher percentage of them where these smoking status and their lighters, whether they have lighters are correlated.
Compare smokers who carry lighter and who don't care, who doesn't carry lighters.
Yeah, so, I think another way of saying that if I stratify, I look at only people who are smokers and then look at the association between lighter and lung cancer. Great, and I can do that similarly for people who are non-smokers. Right, so if you stratify on smoking status here, assuming it's a binary, right, yes and no, whether someone is a smoker or not, you can do a stratified analysis based on lung cancer, and then you can aggregate the results together. And very likely you will see that when you stratify on smoking status, right, among people who are smokers, carrying lighters has a non-significant effect on lung cancer, and similarly for the other stratified group. Great, right? So this is hopefully this gives you an intuitive example of how things can go terribly wrong when you do not control for confounders in a study. And in this case, it's simple because the confounder is just one thing, smoking status, and it's binary. You can stratify, you can aggregate them together, and you will be able to debias the study. Let's now go back to our motivating example of diabetes. In this case, we're not talking about lighters or lung cancer. We're talking about GLP-1 versus DPP-4, and the outcomes acute MI. Those are clear. But what are confounders in this study? What are some of the usual suspects? Yes, please. BMI, great, I have that on my list. I will show in a second. I wish I had an animation to show the ones that people mentioned. Yeah, good. What else? Age, okay, great. Hypertension, fantastic. Yeah, so these are, diabetes is a disease we know we have relatively more knowledge than many other diseases, so we can come up with some good suspect. So I list here maybe demographics, age, sex, some conditions like obesity, diabetes, hypertension, and maybe also some of the lab tests are important, like their HbA1c values, BMI, blood pressure, so on and so forth, vital signs. And George mentioned that right now, if we have a perfect knowledge about what variables are confounders in a study, then we'll just go and phenotype them from the data and we can include them in a study. Let's pretend we have perfect medical knowledge about exactly in this study, in this exposure outcome comparison, we know exactly what the confounders are. Then what do? We build a propensity score model, right? So the propensity score is the probability of getting the target exposure given a patient's baseline confounders, right? They're confounders at the baseline. So it's a probability between 0 and 1. In practice, we never observe a propensity score, right? It's not a feature in your data that tells you, oh, for people look like this person, the probability of getting treatment is 0.78. But this is something that we can estimate from the data. Because we do observe who got the treatment, who didn't, and their baseline characteristics. So in practice, we often fit a logistic regression, and we throw in the confounders as a covariates into that model and use the treatment indicator as the outcome for this model, and we can extract the predicted probability from a logistic regression, and that is the propensity score. Okay, so now we fit a model, a logistic regression, we get propensity scores for every individual in our cohort. How can we use the propensity scores to debias the study? The propensity scores can be used in 3 major ways: matching, stratification, or inverse probability treatment weighting, IPTW. Sometimes people omit the treatment and just call it IPW. So for today's tutorial, I will only show an example of matching because it's much more intuitive to understand. So here on the left, so every pill here is an individual, and their probability is shown as the percentage on that pill. And I have my target cohort in red and the comparator cohort in blue. So what a propensity score matching does is essentially to match let's say the highest propensity score in the target group, or match that to someone from the control group, but also has the highest propensity score that is close enough in numbers, for example. Right, we kind of allow a big margin of error, but let's say we think 93% and 73% is good, close enough, and we'll match these 2 people based on their propensity score. And we do that for every individual in the target cohort, and by the end, we will have our matched pairs of individuals. So what this does is that, remember, right, the purpose of doing this is to control for confounding. And what that means is that we know that some patient characteristics, their distribution are different between the target and the comparator population. So using the figure on the right as an example, if I plot age for the target and the comparator groups before matching, we all see that, agree, hopefully, that there's some differences in the mean age and the standard deviation. And after propensity score matching, this is the plot that we often see, or at least would like to see, is that after matching in this matched population, the age distribution between the two is very similar. Like their mean, their standard deviation is very similar. And in OHDSI analysis pipeline, we have a diagnostic to actually check we call the covariate balance before and after matching to ensure that the propensity score matching is successful, that it balanced all the pretreatment covariates in our study, so that the two groups after matching can be considered exchangeable, just like in a randomized trial.
So basically, each patient should have counterpart.
Yes, yeah, like a matched
In the
counterpart.
exam, they are removed from the cohort. Right?
Yes. Yeah, for doing one-to-one matching, we do lose patients after the matching process. So there are variations of matching, right? Instead of doing one-to-one, maybe you're doing 1-to-2, 1-to-4, 1-to-many. There's variations for doing that. But in our analysis, we almost always just doing one-to-one. If you're worried about losing samples, then stratification or weighting are the usual alternatives where you don't have to lose patients in the confounding adjustment process. Okay, so propensity score is just a modeling technique that allow you to get back exchangeable cohorts on the variables that you pre-specified, the variables that you believe are confounders. And we named quite a few suspects for this study. What are the potential confounders? But how good are we at doing the confounder selection? Right? We can name maybe 20, 30, 50, 100 potential confounders. But if I look at an observational database like an EHR or insurance claims, like an OMOP that follow OMOP common data model, we found in a typical study, we often encounter tens of thousands of concepts, unique concepts. And how reliable can we select confounders from this large pool of covariates? These are some of the usual techniques that people do, right, in the observational study field or in biomedical research with observational data, is that we'll have clinicians in the team, they contribute their domain knowledge. The researchers will also do a literature review to see what others pick as confounders in who study similar questions. And maybe we'll also do some empirical association, looking into the data, trying to assess what variables are highly correlated with the treatment and the outcome. So by definition, they're potential confounders. And oftentimes we use a combination of these. But as you can see, or if you have done observational studies, this is not surprising to you. And you can probably see a lot of problems with this approach. It's not very systematic, right? If you want to run a study across 10 databases that are federated, it's challenging to say how the clinicians from different universities can disagree on what variables are confounders, or their data may be mapped ETL slightly differently from yours. So if you rely on empirical association in your own data, that would not generalize to their data. So overall, this is not a very, I should put the cross earlier. So, so the red block doesn't mean highlighting these. It actually means don't do it. So yeah, instead, what do we do in OHDSI? We use a method called a large-scale propensity score. So we're still fitting a propensity score model, but the difference is in what we include in our propensity score model. We strongly believe or highly recommend to include all pretreatment covariates from the database. And you say, wow, that's many covariates, tens of thousands. You probably don't have that large a sample size. So what do we do? In this case, with this high dimensional data, we use L1 regularization to reduce overfitting so that we, in the case we have more features than sample size, we can still fit a reasonably well and stable propensity score model. So there's many advantages of this approach. The top three that I summarize here being, first, it minimizes the risk of omitting an important confounder since we're including all. Second, it reduces subjective decisions and researcher bias in covariate selection. So it avoids human bias and p-hacking. If the difference between a p-value 0.049 and 0.051 is because of few covariates, then I understand. I've been a student myself in the past, and it's very tempting to choose that study design that gives you that significant p-value of 0.049. And this helps LSPS by including all helps prevent that subjective decisions. And also for federated data network, this is much more scalable and interoperable across institutions and databases. Okay.
Could you give any reasonings on the all covariates except?
Oh, yes. So the all covariates except, I'm glad I put it here. So in causal inference, there are variables that we know should not be included in propensity scores or confounding adjustment. Many of them are post-treatment variables, like mediators or collider variables. So when we say, that's why we highlight all pre-treatment covariates, meaning right, if someone has their blood pressure measured right before treatment and right after treatment, we include the pre-treatment blood pressure and not the post-treatment one, because that could be a mediator or collider. Instruments are variables that are highly correlated with the treatment, but has nothing to do with the outcome. For example, if for a drug that is delivered through injection, you would often find that the syringe, which is a procedure code that's highly correlated with the target drug. If the comparator drug is an oral tablet, then the syringe will be an instrument, but we don't believe whether the syringe causes any differences in the risk of acute MI. So things like instruments, syringes, we remove that by diagnostics when there's a strong, almost like a perfect correlation with one treatment.
What if you, well, it's obvious, syringe doesn't change anything, but if you know that there is something, well, I can't make it up now, but some real covariate and the diagnosis of something that is exactly binded to one of the drugs, like, I don't know, like the same way to give an example, one drug is given as a pill, another is a syringe, and then of course the syringe is associated with one drug, but it doesn't matter. Imagine we have some real covariate that is also associated with one drug, but doesn't matter in general. Can we fine-tune the model before running the study?
Good question. So yes, first, as you can see, it's hard to come up with something that's real but that's not obvious, like syringes as instruments. But sometimes, let's say two drugs are always co-prescribed, then so basically we can, in that case, we kind of need to reformulate our research question or our conclusion, right? The causal effect that we estimate is for those drug combinations, rather than claiming that as the effect of one drug than the other. So that is another cases sometimes we encounter when two drugs are nearly always co-prescribed for some reason. Then in that case, I would argue estimating a causal effect for the drug combination is good enough if the drugs always give together in practice. what is really the additional value it brings that you have to know exactly this drug, but not the other one that's always co-prescribed. Yeah.
So the rule is you never change the all pre-treatment covariates. It's like the method, it's like hard-coded and you don't change it. Right?
That's the,
Yeah, so you basically have two options. One thing is that you can redefine your target comparator. You believe that the thing that's highly correlated, you can't separate it out like it's co-prescribed. And the other is you can actually choose to remove it from the model. Like the syringe, you would just remove it from the dispensing model.
yeah.
So the diagnostic would tell you, oh, the syringe is highly correlated, and then you have to decide based on your domain knowledge which of these two actions. Oh, and there's a third action, and that is, okay, now I'm in trouble because I don't believe I can do any of those two things. And now I'm.
Okay. Okay, so you basically can remove one of the covariates if you. I think we have even parameters. Yes. Can I ask another question?
Yeah, of course.
Okay, if I'm asking a question,
Yes. I leave plenty of time in my part for questions.
Okay. So like you said, if the population number is lower, maybe I didn't understand that, but population is small enough that you can't use all covariates, then we do the regularization. But how is it, like we have like 1,000 of covariates or 10,000? It doesn't matter if the population is big or not. Like how is it dependent? Like, because yeah, like how does it work? I can't imagine myself.
Yeah, so regularization can work to some extent, but if you only have 10 patients in your cohort, then there's no magic that can make it work to include
Okay, I got
like 1,000 times more covariates than sample size.
In non-regularized regression, if you have, let's say, 100,000 covariates, you have 1,000 patients, you can't fit the model, you don't convert it. That's the regularization.
So if you have like 1,000 patients and so many covariates, just model can't, because they will be still so high variability. Because if you have 10,000, there will be high variability. If you have 1,000, there will be much less variability and probability of patients are different. Okay, I see. Okay, got it.
Yeah, so we did do studies to kind of see where the method breaks, and we did find in the lower hundreds, we start to see, from repetitions, maybe some rounds the model doesn't fully converge. But if you get a few thousand patients, then we haven't really seen much challenging in fitting these models. Yeah, question at the back.
Yeah, I have two questions.
Sure.
Yeah, first is, this is a large-scale permanent score, you just all the covariates from the database. I still have the risk that I missed the key to compound, the confounders not including the database. This is Mr. Mark on that. The second is, if you bet on a large scale permanent score, selecting that order, lastly, actually reduce the dimension of this. It's a little, sometimes the variable selected is hard to interpret. Yeah, it's from the epidemiology, you really want to interpret this as each risk factors before they run from the score for this. And then when you face this is the time, how can you interpret that? People are asking the variable, including the model. Some people think that don't make sense, or something. It's hard, it's difficult for me sometimes.
Great. So to answer your first question, this actually perfectly brings me to my next slide. So we have a lot of diagnostics. Here's just a very quick overview. My faculty colleagues will go into the details of these diagnostics to assess still, right? Even though I include all 50,000 covariates in my propensity score model, but what if there's still just one variable that is not measured in your database, and that could potentially cause risk confounding or bias? Is there any diagnostics to assess that residual confounding? So I'll leave that to my Tara. To answer your second question, yes, when we fit lasso, then the regularization would choose some covariates and not others. it is often framed as a covariate selection or variable selection, and many people use that for that purpose. In our case, we do not. So it's based on correlation in the data, and it will, if there's variables that are correlated, then lasso will pick one and not the other. We don't have control over that. And I think your question is really about the interpretation. What if some variables get selected but not others? I can see this in epidemiology, or if you want to understand the treatment policy or mechanism, then that can be very useful information. In causal inference, if our goal is to prevent bias in the study, then we don't really overinterpret what gets selected or what does it mean why this gets selected. We use diagnostic like covariate balance just to make sure that it doesn't matter what variables get selected. When we check covariate balance, we check for the selected ones and as well as the unselected ones to make sure that they are balanced between the treatment and control. George, would you like to add something?
Yeah, I mean, exactly. Basically, we're not trying to identify the confounders. Mm-hmm. What we want to do is make the two groups equal. And we don't care if lasso picks this variable or correlated variable, because we're not, if you want to know which one of the confounders, then you should do a different study to find the confounders in which you iterate through all the variables and find the ones that are associated with both the treatment and the outcome, which is a very expensive, hard procedure to do. But that's how you find the confounders. And the ones we caution people not to look at this as confounder selection in lasso. It's merely the most efficient set of variables that can make the two groups in each of their entireties be balanced. And then we double check that they're balanced with the diagnostics afterwards. So that's our answer. And in fact, if we had infinite data, we wouldn't use lasso to select the confounders. We would just use linear regression and balance the two groups that way. So lasso is just dimension reduction for the purpose of dealing with the fact that we don't have an infinite data set.
Yeah.
Yeah, I've got one last question on the last slide. Sorry to make you go back.
No problem.
But on the all covariates except part, like in the slide prior to this one, you said like you don't want to have as much domain expertise, literature review, what PHAC can supervise, et cetera. It does seem like for all the except covariates there, you do have that domain expertise. Like, is there any automated way to do this, I guess, to remove those covariates that you know should not have, whether they're instruments or anything else?
Yeah, maybe just to clarify, when I say don't just rely on domain knowledge, right? But you should have clinicians in your team when you design a study, and we always do in that case. And hopefully for syringe to be an instrument, we don't need expertise too.
Yeah, I work with like the EHR, so all the covariates, so I'm trying to figure out which ones should I be looking for access in general.
Absolutely, yes.
I have access clinicians, but
So to be clear, for the most part, this is fully automated. It's just these exceptions when all of a sudden the syringe pops up in diagnostics, it is a highly correlated, then somebody needs to look at it. But like we do like thousands of comparisons, and let's say like 5% you actually need to intervene.
I think we have a question there, and then we'll take one more from the back.
So do you do anything to account for temporal variability? Like if treatments change over time, or is there a recommendation for the maximum amount of time that you can do to cohorts that you construct?
You mean like if they started with one drug, switch to something else, what to do in that case?
Or like, do you account for like literally 2 calendar years or 20 calendar years? Like over time, as treatments and data vary, how do you account for that?
Yeah, so if for the own treatment design, then we take into all consideration all these things that can happen post-treatment if they switch drugs, if they leave our healthcare system, or if they leave for, there's like a gap in their records. Then usually if you do a own treatment design, then your follow-up won't be 20 years. It may be a few months, a few years, but it's unlikely to be 20. And for the intent to treat design, then sometimes for a database that's 30 years long, then you could end up having a very long follow-up time in that case, yes.
But as far as if you were mentioning calendar year, like that's not a covariate. So,
It is,
so I'm going to balance on that.
Okay.
So I'll end up with an average. So if the treatment effect changes over the years, I'm going to take an average over those years. But the good news is my two groups will be balanced for that. So I have a true causal effect, but my estimate will be of the average over those years, however they end up balancing.
Okay,
Yeah.
that makes sense.
Thank you, George.
Thanks.
I didn't quite realize that that was the question you're asking. Yeah. Yeah, please.
My question is a bit of a clarifying question on the balance, the propensity to be exposed, right? Because that's what we're trying to get the balance on. And sometimes you may have, even though you sort of have a similar score, there may be like differences in the distribution of the things that created the score. And so even though we're not chasing confounders, I guess the question is sometimes if that prevalence of that one of these things are small or it's really kind of skewed, we often would end up including it, and I'm wondering how does that get factored into like this description?
Well, really, when we do balance, I mean, we're checking, we literally check for balance in all 60,000 variables individually and take the maximum balance. And if it's over 0.1, we reject the study. So we're pretty rigorous about that. So we do care about every last variable. So on average, I know that one score is a 58.58 for these variables, one's a 0.58 for different variables. But if you do that over the whole population, we can show that you'll end up with two balanced groups. But, as the variables get small, you could have some imbalance. But that's where you do standardized mean difference. You divide by the standard deviation, which is affected by the prevalence of the population. But the important point is that we're actually checking balance in every single variable, one at a time, 60,000 of them, make sure all of them are balanced. And then we're getting that to work most of the time. But you do achieve balance. What we're finding is when you pick 20 variables and you think are confounders and try to balance them, they don't even balance the 20, never mind the other 60,000. When we try to do all 60,000, we actually balance those 20 plus another 60,000 of them. We actually achieve better balance by doing the whole thing. We're finding. I don't know, because our databases are bigger with more stable estimates, but and we do have this hard diagnostic of 0.1 or 0.15 in some of the 0.1, 0.15, whatever threshold you pick on the way into the study.
So you can have the other question, which is like, how big does your sample have to be for that to hold true? Because in smaller samples where we've done it, as small that looks reasonable and no one flinches when we submit it for publication, but the truth is that it truly pan out.
So we just published this. So for say 50,000 variables, if our total sample size is 4,000, so 2,000 and 2,000, that works pretty well. As you get smaller than that, you get more chance of balance. So we have a new threshold which adjusts itself according to, as your sample size gets smaller, your confidence gets bigger, so you can accommodate more confounding. So we have an algorithm now which changes the threshold a little bit according to the sample size, and then we get down to 500 total sample, 250 in each group, balancing 50,000 variables, and are getting results with nominal type 1 error rates approximately the p-value 0.05. So that's maybe just got published in statistics of those.
I would say the others, right, the lowest bound for applying any of these methods is now we have around a couple of hundred.
Yeah.
The minimum number of patients that you need in your cohort to be able to do it. Fewer than that, you probably don't have enough high.
You need a couple hundred in each group. And 250 in each group is good. Once you get to 125 in each group, that's where it doesn't. That's pretty small.
Like how precise we are, 125 in each group, that's where the things start to freak. Yeah, thank you so much. So this is my last slide. Thank you all for your great questions. And a lot of questions alluded to the diagnostics that we have in the OHDSI ecosystem and the names that I also put on the slides, like negative controls to assess unmeasured confounding bias, right? What if there's a confounder that's not recorded in my database? Covariate balance on all the 60,000 covariates, as George mentioned. And also there's another assumption. This is the most famous assumption called unconfoundedness, ignorability, or exchangeability. It's basically about, right, is there still residual confounding in the study? And we have diagnostics for that. There's also a less well-known assumption, which is equally important, called a positivity or overlap. This is the case when, you know, you have two groups that are just too different that you're not able to make them exchangeable no matter what you do. So, like, are you in that situation? How can you tell? So, and we do that through a visualization of the propensity score distribution and looking at overlap between the two distributions of propensity scores. And there's one, just for completeness, I include the Suva assumption here, which is a terrible name. It doesn't really mean much, but it basically means that there shouldn't be any interference between individuals, like, you know, infectious disease is a classic example that is violated. And consistency, which means that there's no hidden variation of the treatment. Your treatment is well defined, so that with the estimate, the causal effect that you estimate you can contextualize that well with no ambiguity. All right, so that's my part. Thank you.
Yeah, so we're here, the interactive. So what I'll try and do is just, now that you've seen a little bit how our approach works to effect estimation, I will walk us through basically trying to think through a design of our own and have you weigh in on the decision. So of course it's called interactive, so feel free to shout out and let me know what you're thinking. So we'll use the question that George already introduced. For patients with essential hypertension, do ACE inhibitors compared to ARBs decrease the risk of acute myocardial infarction and angioedema? Sorry, it should be angioedema. Yeah. So the first thing we have to do, I'm still selected there. First thing we have to do is we have to fill in the template that Linying showed you. So let's do that. So I'm sorry I didn't keep the slide on with the question, but I hope you memorized it. It wasn't that hard. So again, what is, and I'm going to start actually with the target and the comparator. What is the target drug or the target exposure that we talked about? It's a very simple question, I think. We can go back to the previous one. What's the target? ACE inhibitors, yes. What's the comparator? And what is the outcome? Yeah, in this case we have two, and both of them are good. And what is our time at risk? Linying outlined that we have two main ones on treatment and intent to treat. Which one do we want to take?
All of it.
All of it, sure. Well, in this case, it's so. Let me show you how I filled it in. So ACEs versus ARBs. I'm sorry, I screwed these all up. These are right actually. Well, so ACEs versus ARBs, so that's the target, that's the comparator, target comparator. In this case, I split it up by the two outcomes. I'm here defining a on-treatment time at risk, so while exposed to the drug. Yeah. You could wonder, like, I actually had to look it up. Angioedema is not considered to be acute, but other, like anaphylaxis, had the outcome being anaphylaxis, then we might actually say, well, I don't care about the full period when people are on the drug. You get anaphylaxis in the first couple of days, or probably the first hour or not. So then I might actually redefine my time at risk as just the first few days. But in this case, like angioedema is considered to have a constant, you have a constant risk of it. And actually, acute myocardial infarction, you would expect that the drug over time protects you against cardiovascular events like that. All right, so as you noticed in the template, you have to define both the target and the comparator. So why do we not have an option to not pick a comparator? So here the question is, why are you required to fill in a comparator? Is the answer A, it's a limitation of the OHDSI tools. They are free tools, so what can you expect? Better tools would allow you to do that. Or is it B, there are fundamental problems with a no-use comparator? Everybody raise their hands. Who says A? Or who says B? All right, so yes, that was of course a trick question. So anybody have an idea of what a problem could be with a no-use comparator?
Yeah, because it's not fair to not give treatment to people.
Yeah, so I think what you're trying to say is that those people could be very different. So that is one major reason is if you take a no-use comparator group, well, then you're comparing people that are sick enough to actually need a drug, and you're comparing them to people who are healthy enough to not need a drug. So that's a big problem, but that might be actually something that the tool would solve for you because the propensity score would show that, and probably actually you would end up with no people to match. Also, another really basic problem is, well, what is the index date of the comparator group? Because you remember Linying telling you about the time machine. Well, what is the point in time that you would have to travel back where the people did not take the drug? If you could accurately find that point in time where, okay, these people, they were thinking about getting the drug, but they didn't get the drug, that will be the right index date. But that's not recorded in your data. So then people start to do awkward things like, I'll take the 1st of January of the year, but then, yes, that's in the middle of the winter. So now you're comparing people across all seasons to people in the winter. Like it just becomes very intractable when you have a no-use comparator. So even though that's what a lot of people want to do, and it's like, in a trial I can use placebo, but it's not something that's very easy to do when you have an observational study. So just warning you that probably don't want to use a no-use comparator. Yes, go ahead.
Can we randomly choose the index date for the no-use comparators? If we considering their like race, gender, age, something, and then we do want to compare somebody taking this medication and somebody doesn't take this medication. So for those people who don't take this medication, it is an issue that how I will define the index date. Then we can either randomly take the index date for those no-use comparators, and then we balance these two groups on their demographic characteristics and some communities.
Yeah, so I've actually played this game for a little while. I'll try to make a no-use comparator, and I thought you at least have to go see the doctor because that would be fair. Because else, if somebody doesn't go to the doctor, then you don't see any events for them, and then you can use a propensity score to balance them. It's just very hard. First of all, you lose a lot of people. You have to nest it within the people who have, in this case, hypertension, of course. So I even did that. And then I could find people that were matching. But then if I use negative controls, which we'll explain later, I actually saw that you still end up with too much bias to actually get a good estimate. So because I think it has to do with the fact that just any random date is not the date when the doctor decides to give you a new treatment. That's the big distinction. But yeah, we have diagnostics, and they would actually tell you that what you're doing either works or doesn't work. But in my experience, it doesn't work. But the good thing is the diagnostics will tell you. If the propensity score doesn't tell you that you can't find matches, then the negative controls will end up telling you that there is too much residual bias that's remaining. So you're welcome to play the game. I'm just saying be very careful with it. Yes?
Instead of a random date, you use a state like a pregnancy. So the start of pregnancy before
Well, so the thing about a causal inference is that it's basically the inference of a decision that's being made. So if your index point is the end of a pregnancy, well, that's not a choice. So that's a bit of a hard thing. Like, what are you then evaluating?
Practice, a clinical practice. The use of antihypertensives in pregnancy, for example.
Well, but then what would be the index date? Is it so the index date is the end of pregnancy, and the treatment is whether or not they used hypertensive during? Yeah, no, I'm trying to think through. Yeah, it's problematic. Like I said, it's not the point that you're choosing is not the point when the decision was made, and so now you can have trouble that the decision was in the past and that there could actually be intermediaries included in your propensity model. So it makes life very, very complicated. So in general, try and make sure the index date is the date of a clinical decision that you're actually trying to evaluate the consequences of the decision. But that's a good question to try and help clarify that. Thank you.
A real study that I wasn't trying to work on and stopped because I ran into this index date issue. I mean, the non-comparator, like index date stuff makes sense when your exposure is a drug. I was looking at my PFX, so it's AFib on like stroke later down the line. So AFib was my exposure. And then I was like, okay, what's my index date for my control group? Oh, I don't know. Just like pick a random date the same year. Do you have any thought to motivate that question a little more? Because I was like stumped and just kind of gave up.
Well, yeah, so that's another interesting question a lot of people have. They want to study a disease and the causal effect of that. And again, that's usually not a decision. So whether or not you have AFib is not a decision. So it's hard then to define what the counterfactual is, like the decision to not have the AFib. So, and as a consequence, you then have a problem identifying the index date.
So is causal inference typically only used when decisions are supposed to be made, not trying to look at causality generally? Or
I think that's a good, unless the exposure is really external, then you might do it, like getting hit by lightning or something, but. All right, any more questions? Let me see how I'm doing on time, because we do have a break coming up. All right, so now I'm going to go a little bit deeper into actually the phenotyping that George also alluded to. And just thinking about how would we define our target and our comparator and our outcome, because all of those would be cohorts or phenotypes. When we define a cohort, basically we have to think about three things. What is the index event? So what is the thing that has you enter the cohort? What are inclusion and exclusion criteria that we then apply based on that event. And then we also typically have to think, well, when would you actually exit the cohort? All right, so for our ACE inhibitor target cohort, what would be the index event? When do you think people should be considered entering the cohort of ACE inhibitors users? Like think of the CDM and like what data do we have available? Like what occurrence in there would you say would be the index event?
Earliest drug exposure of AC.
Yes, but I don't think you're supposed to make comments because you're a frequent user of our tools, but no, you're absolutely right, yes. So yes, the index date in this case would be the first occurrence of a drug exposure record of any ACE inhibitors. And so we can probably make use of the vocabulary and pick ACE inhibitors and all their descendants and just create a cohort definition that says take the first one of that, and that's going to be our index date. Yep. All right, so what kind of inclusion and exclusion criteria might we want to have for our group of ACE inhibitor starters? No thought? Could be none, but...
Exclude the people on ARBs.
Exclude the people on ARB. Okay, I'm going to table that for a second. But it's a good point. I'll actually explicitly call it out later. Maybe you want to restrict specifically to people with essential hypertension. Could be or could be not. If they're like ACE inhibitors don't have other indications, that we might actually not need that. But it usually is recommended that you actually restrict to within a specific indication that you want to study. When do we exit the ACE inhibitor cohort? Death, yeah. Oh, yeah, in general, I would say end of observation period is probably a good point to end, which hopefully is at death. But any time before death when we would exit the ACE inhibitor user cohort? Yeah, last day of data available. But also, like... Switch? Well, switch is a hard one, actually. But yes, no. Well, so typically what we do is when you stop taking the drug. So you know, when you start the drug, and then we usually have like a duration of exposure. So we have a drug era start and end date. We typically allow a small gap where if you see a new prescription within that gap, then we say, oh, probably you were continuously exposed. And if we then see a gap that is bigger than let's say 30 days, or we don't see any other prescription anymore, that's when we say you stop taking the drug. So that's typically what we do. You start when you start taking the drug, and then when we believe that you've run out of prescriptions, basically, that's when you end. All right, for ARBs, what is the index event? Yep, first exposure to ARBs according to the drug exposure table. What? Sorry? Oh, okay. Inclusion, exclusion criteria. Any thoughts? Well, it doesn't matter, but what you choose, it better be. Oh yeah, go ahead. Allergies.
Because allergies is a pretty common reason to get one versus the other. So if someone's allergic to the ACE, they're never going to get the ACE.
All right. So do we just exclude those from the ACE cohort? Or maybe also from the ARB cohort?
The problem is a lot of people get them sequentially, right? There's an index there. So there's a prior exposure. So actually, this is harder to define with the ACE.
Yeah.
Ideally, you want someone who started on an ARB, not on an ACE, and then switched to an ARB.
Yes, we'll actually get to that in a minute as well. But one point I just wanted to make is whatever, I mean, you have to decide what your inclusion and exclusion criteria are, but what you want to make sure is that they are the same for both of these cohorts. Because if I start to exclude people who are allergic from the one cohort, now I've created a difference between the two cohorts that's not just a drug. And now if I find an effect, I'm not sure whether it's caused by the drug or it's because I was comparing non-allergic people to a mix of allergic and non-allergic people. So you have to make sure that those two cohorts are identical in those senses. And we'll get to what you do with overlaps and sequences of these two drugs. All right. So now the question, what should we do with the people who use both ACE inhibitors and ARBs, not necessarily at the same time, but somewhere in their record? So do we, A, create exclusion criteria that remove them from both exposure cohorts? So in the ACE cohort, we remove people with prior ARB, and in the ARB cohort, we remove people with prior ACEs. Or actually, that was B. A is, do we just remove them completely? And C is, do we trust the OHDSI analytics to solve this for us? So who thinks, A, we have to completely remove people who at any time use both ACEs or ARBs? Nope, nobody thinks that. Who thinks B, we add it to the cohort definitions and remove them? All right, and who thinks C? I have some trust, at least, here in the OHDSI tools. So the thing is, I would recommend using C, although B would work. So basically, in the CohortMethod tool, there is an option where you can specify either implement option A, just remove people that have both exposures, or B, take the first. But what is an advantage of not baking it into the cohort definition is that now you have a cohort definition that you can actually reuse. Because I'm comparing ACEs to ARBs, but if I now in ACEs explicitly make the restriction that they can't have prior ARB exposure, but now I'm going to compare ACEs to beta blockers. Well, now I have to create a new ACE cohort that excludes them, whereas if I rely on the CohortMethod package to do this for me, I can just keep on using the same ACE inhibitor cohort, and I can switch out my comparator without having to change the cohort definition. Yes?
Yeah, I guess it depends on how many patients we receive the book. If only very few, I think choose the A to exclude them. Right? If there's many, maybe to have another option D, you could create a third cohort that patients receive the both.
Oh, you mean at the same time? Or?
Yeah, I mean, it depends on how many patients they receive the both, right, etc.
Well, if it's at the same time, you could create a separate cohort just for that, yes. Yeah. Which we have done actually in some of our studies. But yeah, then you need lots of data to be able to do that. But then the question that you're answering, of course, changes. Because if I have one cohort that is both ACEs and ARBs, and I compare it to, let's say, ARBs, then now I'm comparing those two treatment options, which is a valid question. It's just a different question than mono ACE versus mono ARB. Yep.
Yeah, but what OHDSI tools does in this case?
So you can choose. You have actually three options. You can remove them from both. If a patient has both exposures anytime, you remove the entire patient. Option 2, which is the most used one, if they have two exposures, you keep the first one and you censor when they get the second one. And then the third one is you keep both, but now you have a weird situation where you could have the same patient, basically ER analysis twice, and well, you could remove the overlap time, but that's still, it's not something I would recommend.
So basically, by default, there is censoring on when the other drug is added.
Yeah, it's not by default, but it's another switch you have to turn on then if you do that. Yes.
It doesn't happen automatically, you get the choice.
You got the choice, yes. Yep. All right. All right. I think actually we'll skip over this. Let's go to the outcome cohort, acute myocardial infarction. So we need to create a cohort. What is our index event? When do people enter this cohort, acute myocardial infarction? Think about the common data model. Where would you look for finding people who have a acute myocardial infarction? Condition table, yep. Which condition? It's not hard. Acute MI, yep, acute MI and any of its descendants. Do we maybe want to make this cohort definition a little bit more complicated? Any diagnosis of an acute MI? The first one, yeah, but yeah, inpatient or emergency room, that's what we typically do, because then we believe that we have more trust that it's actually an MI. Yeah, so these are all things you could do. When do we exit the MI, acute MI cohort?
After discharge?
Yeah, well, usually, hopefully, an MI doesn't last very long. So actually, in this case, it doesn't really matter because we tend to use a time to event model. So we just care to when it starts. But I would probably set it at the same date. Like you have your MI, and then hopefully at the same day it's resolved, or else you probably are dead. Another important question is, what is the minimum gap that can exist between subsequent events? Because that's a problem with our data, is that somebody goes to the doctor, maybe they have an MI, and then you record that they have an MI, and then a week later they go back and the doctor checks on the patient to see whether something is still good, and they say, oh, it's still good, but you came here because of your MI, so now I've recorded that in the data, and it seems like they had a second acute MI. So we typically allow for a gap between events, which we call the clean window. So what would people say would be a reasonable gap or clean window that we would allow? I don't think actually there's a really good answer, but okay, Dima, what would you do?
30 days?
30 days, yes.
Maybe even more because they have follow-up events, follow-up visits. But yeah, first comes to my mind 30 days.
30 days. I think, yeah, probably something like that. Like I said, there's no real good answer there. Go ahead.
I just have a question about like defining an outcome cohort. So I'm used to sort of looking for the outcome in a cohort that has the treatment or exposure. Here, in like the OHDSI framework, would you, when you're talking about inclusion and exclusion criteria, would you do anything related to your treatment?
All right, so that is actually my next question somewhere. Well, no. I thought I had it somewhere. Oh, here, yes. Would you restrict the outcome cohort to the people in the exposure cohort? A, yes, or B, no, trust the analytics to do this for you. I'm not going to have to answer this. The answer is, or at least, oh, did it switch? The answer is, or at least I believe the answer is B. It just keeps switching. Yeah. That no, you should trust the analytics to do this. And it's the same reason why you don't need to exclude the other drug, is if you just define your cohort to be acute MI, and then the software would just take the exposure cohort and basically only take those people and then see who of them are in that cohort. Now you have a cohort that is reusable all the time. Like we have a acute MI cohort in my company that we just keep on using over and over again for any drug that we look at. And so it's a very powerful thing now. We have a whole library of these things, and we have like week-long debates on what the right way is to define this thing is. But once we define it, we can reuse it in every study. So you don't have to restrict it.
But just clarify that if you're writing an ARM program, yes, you're going to do this. The point is the OHDSI analytics do this for you, and here's why we do it for you for the reason you just said.
Yes.
So it's not like a no, it's a yes, but let OHDSI do it for you.
Correct, yes.
But it's not let OHDSI do it for you, it's you will do it in OHDSI instead.
Yeah.
Yes, but you don't need to do it in the cohort definition is the point. Yep. We're actually running a bit short on time. All right. We actually covered the propensity model. This thing's lagging. That's of course this is showing. Sorry, it's on presenter mode. No, I want this one. Why is this not the same as that? This is what I wanted to say. All right, so what? Sorry, there's a lag here. So what was up there was not on here on any of it. So we talked a little bit about the covariates and that we basically don't want you to pick covariates. We want the lasso, the regularized regression to do this for you. Except one thing that you do need to do is you need to exclude the drugs that you're studying. So that's something that you manually have to do. And the reason why is because the propensity model includes everything before up to the actual exposure. Because the day that you're getting the drug is probably there's a lot of information on why you're getting the drug. So we don't want to ignore that. But that also means that the drugs themselves are going to end up in the propensity model if you don't explicitly exclude them. So that's then going to give you a perfectly predictive model because to predict the drug, you just take the covariate that says that it's a drug. So that's like a manual step that you have to do. And then I also mentioned a little bit about negative controls. These are, I think, very important to evaluate whether you have bias. I will go into negative controls a little bit more later on. But basically, we were looking for outcomes that are not caused by either ACE inhibitors or ARBs. So let's just do a brief show of hands if you think something is a good negative control or not. So it cannot be caused by ACE inhibitors, which means, or ARBs, means it also cannot be prevented by ACE inhibitors or ARBs, but it has to be a causal relationship, not just an association. So let's just quickly play this game and let's see if you can see how it goes. So contusion of knee is a negative control. Who says yes? I think it's yes, yeah. It's hard to imagine how these drugs could cause that. Hammer toe. Yes, I think so too. Heart failure. No, because these are antihypertensives, and the idea is that they prevent heart failure, so there's a causal relationship. Foreign body in air. Yes, it's like somebody sticking something in the ear. Opioid abuse. I see some hands and some hands not. I'm not 100% sure, so why don't we then just leave this out of the set? If there's anything that we're unsure about, we just leave it out. Poisoning by tranquilizer. I think so too. Coughing. Very good. That was a trick question, because one of the adverse events of ACE inhibitors, I think, is coughing. So that's definitely caused by the drug, so we shouldn't leave it. All right. You all get an A+. All right, so ultimately what we now did very quickly is we defined the inputs for this software program called Strategus that Linying and Tara also will run you through. A target cohort, a comparative cohort. I skipped the indication cohort for time, but you have to believe me. Outcome cohort, the time at risk, the covariates to exclude from the propensity model, and then a set of negative controls. So this is literally all you have to define, and then what you get in return is a standard set of outputs. So we actually get a full characterization package. You get instance rates for these outcomes. You get de-challenge, re-challenge statistics. You get patient characteristics for the people that take the drugs and the people who have the outcome, and people who take the drugs and have the outcome. We fit prediction models, but most importantly for this course is you get estimation results. So you get a full cohort method result, comparing ACEs to ARBs for these two outcomes, fully propensity score matched and with negative control evaluations, objective diagnostic and everything. You also get something called the self-controlled case series design, which is another way of answering causal questions, which actually can compare to no exposure. All of that with full diagnostics to evaluate key assumptions, including negative controls. So you had to put in some work, but then you're getting a full package, and it's the same package you get all the time. That we believe is very helpful to answer your causal questions. And with that, I will no longer hold you from the break. Unless there's a question, well, anyway, then just come up to me during the break. All right, thank you.
I hope everyone had a nice break. We'll come back together now. So my name is Tara. I'm a PhD student at Columbia, and I'll be doing a little bit of a recap of a lot of things that have been discussed earlier today, and we'll kind of now have an eye really explicitly towards how do we use everything that we've learned and have been talking about so far and actually apply it so that we can implement a study. And so we'll walk through a full kind of tutorial in a little bit more depth later, but we'll look specifically about how do we translate these kind of concepts about study design into code that we can eventually run. Okay, so this is where we are. And so we've kind of talked about, you know, the comparative effectiveness study design at a little bit of length. We know that we have these different cohorts that we define. Specifically, we're comparing our target cohort that's receiving, one drug to the comparator cohort that's receiving the second one that we're comparing to. And we can think of each of these cohorts as coming from a larger population, which we kind of touched upon, which is the indication population. So that might be the population of people who have hypertension, and the target is the ACE inhibitors, the comparator cohort is the ARBs. And then we have this fourth cohort that we define, which is all of the people who experience the outcome of angioedema or acute myocardial infarction. And now we know that through kind of our study design, we follow these target and comparator cohorts forward, and we see which subjects also become part of that outcome cohort later. So if we want to actually now implement this, there are a few different pieces that we need to develop first. The first of which we talked about in a little bit more depth with Martijn, is we need cohort definitions for each of these cohorts. And so sometimes we pull out the indication population explicitly and we define a cohort just for that indication. Other times we might embed it into the target and comparator cohorts, where maybe we make a criteria that the patient has a diagnosis of hypertension in addition to taking the target or comparator drug. And sometimes when we separate it out and we have the indication cohort defined separately, that just helps with usability. We can reuse those cohorts and a little bit more easily. So first we need our cohort definitions, as we talked about earlier. Then we need to kind of make these decisions that we were thinking through with Linying and Martijn a little bit about the timing, the clean window, the time at risk, all these different pieces that we're talking about. We need to make a certain set of decisions. So that's the second kind of piece of information we need. And then the third piece of information that we need, or the third thing that we need, is a method to address confounding. So that's what Linying discussed earlier with the large-scale propensity score. So that's the method that we'll use to address confounding. The workflow that will kind of follow, shown in blue, the first thing we'll do is we'll define our cohorts, as we talked about. Then we'll need to formally define this analysis specification somehow. The third thing we'll do is we'll actually run this study. We'll use large-scale propensity score to do our confounding adjustment. And then the last thing we'll do is we'll evaluate diagnostics. And so we'll talk a little bit more. We've kind of already hinted at the diagnostics and why they're really helpful. And we'll walk through the 4 diagnostics that we use in a little bit more detail here. We will use Strategus, which Martijn kind of talked about earlier, to actually implement this study. Strategus is really helpful because it allows us to generate a JSON file, which will include all of the details for our study analysis. And so you, as the designer of the study, will develop this JSON file using some tools that we have. And then that JSON file can be shared with any other site in the network that maybe you want a certain partner to run that study as well on the network, and we can now put those results together in a meta-analysis. And so it's really easy now to do this analysis at many different sites by sharing this JSON file. So that the OHDSI tools that we'll be using, first to define the cohorts, we talked about Atlas, and Caper is another tool that can be helpful. And then there's a script in the Strategus repository called downloadcohorts.r, which allows us to pull down those cohorts that we've defined in Atlas and embed them into the JSON file that we'll create. The create analysis specification.r script will allow us to create that JSON that we've talked about. We will explicitly encode all of these design decisions that we'll make in that file, and then we'll generate the JSON file that includes everything we need to run the study. The script Strategus code to run is the code we will run. It takes as input the JSON file that we've defined, and it will give us all of the results that we need, including diagnostics. We can take these results then and put them into our Schuemie app, which will make it really easy to visualize everything that we've generated and evaluate our diagnostics using the kind of graphics that are generated. So we'll walk through each of these steps a little bit. I might recap some of the details of the choices that we'll make. I'll just show also, so this is kind of the GitHub repository, which has the template for the Strategus study. And so this is exactly what we'll be using when we run our studies together. And so the kind of 3 scripts that I talked about will be here. And then there's also some, folders and infrastructure, which will be handled automatically. And I'll talk through which files we'll actually be editing when you're designing the study. Okay, so first we talked about we'll be defining the cohorts. I won't speak about this in any more detail, but you'll go to Atlas, you'll design your cohorts, and then we'll go to this script, downloadcohorts.r. And so you'll see here there's this link, base URL, and so that allows you to put the link to your Atlas wherever you've defined it. Maybe it's Atlas demo, maybe it's an Atlas instance you have at your site. Wherever you've defined your cohorts, you put that there. And then you list the cohort IDs that you've created, the ID in Atlas that corresponds to the cohort that you've created. And basically what this script will do is just connect to Atlas and download those cohort definitions in a way that we can use them in our JSON script. So this is the first script you'll be editing and running. Oops, went too far ahead. So then we'll move to specifying our analysis. And so they're kind of, we've defined these cohorts in isolation. And when we think about the analysis specification, we're thinking about how do these cohorts kind of relate to one another? And what are these design decisions that will also help us to address sources of bias? In addition to the propensity score analysis, this step, as we've kind of discussed, is really critical for eliminating bias. And so, some of these decisions we've already talked about. Are we going to look at a common period when both drugs are offered? What do we do with subjects in both cohorts? What is our clean window? How do we define our time at risk? How are we going to use the propensity score? In what way? What is the outcome model we'll need? And maybe there's some other data refinement we'll do. And so we'll talk about each one of these and see in the code what are the changes we need to make to implement these design choices. Okay, so the first question about restricting to common period. So we spoke a little bit about that. Sometimes there are certain drugs that are offered at different times, and it might be helpful for reducing bias to look at a time period when both of those treatments are on the market. Maybe there's some critical change that's happening in this time period and the data distribution changes, so we're really only interested in looking at the time when both drugs are offered. The way that we actually implement this now we're in the create analysis specification script, we'll look for this little flag called restrict to common period, and you can set that to either true or false. I think our default is true, but there might be some instances where it's appropriate to set this to false. I'll say that this parameter is a little bit deeper into the analysis specification file because it's not one that's often changed, but I want you to know that it's there if you find it relevant for your study in the future. Next, we spoke a little bit earlier about this, about the removing duplicate subjects. And so we said that there are kind of a few different options to how we handle this. The first one could be that you remove patients who are in both the target and the comparator cohorts from the study altogether. They end up in neither cohort. Maybe we keep all of it and they're allowed to be in both the target cohort and the comparator cohort, even with these overlapping times. We might choose to keep only the first exposure that the patient has. So if they're in the target cohort first, they're dropped out of the comparator cohort and left in the target cohort for the full duration of time that they are getting that drug. And the last option is that we might censor at the new risk window. So then you can see in this case, that's the fourth option. The patient is in the target cohort up until they begin to receive treatment for the comparator cohort, at which point they're censored out of the target cohort, and then they just are in the comparator cohort for the rest of the time. So you can choose how you do this. Our default is that it's keep first is our default. And again, this is another parameter that's kind of buried deep. Many people don't change this, but if you want to, you can. And you just have to find this flag that says remove duplicate subjects and change accordingly to remove all or keep all or whatever it is that you're doing here. And this one that's not often changed. And again, this is in the create analysis specification script. So that's the one script we're working in. We spoke a little bit about the time at risk, when might the outcome occur. And so we talked about on treatment and intent to treat. And so that's kind of the first bar, time at risk, where it says it starts at cohort start and it ends at cohort end. That's the on treatment design that we spoke about. The third one is intent to treat, where we're looking, the time at risk starts when you enter the cohort, and we're looking now to the end of observation. You might choose to do something else. Maybe you're looking at a fixed period after the patient starts taking the drug, say a month out. So that's kind of the second option that's listed there. You're looking from the time the patient enters the cohort and you end at 30 days after. So you could do anything. You know, the world is your oyster. The on treatment and intent to treat are kind of the standard analyses that we do, but you can customize this depending on your case. The way that we implement this in code is by using a start anchor and an end anchor. And so that's what's shown in this table here. And then we can have this adjustment from the anchor to kind of get to exactly what you need. So for the on-treatment design, that's the first row that's shown. The start anchor is the cohort start. The end anchor is the cohort end. And the risk window end is 0, meaning we're not adjusting from the end anchor at all. In the second case, where we're looking only 30 days out from when the person entered the cohort, now we'll use, again, cohort start as our start anchor. Our end anchor will be cohort start. Our risk window end is 30, meaning that we're adjusting 30 days out from that end anchor of cohort start to get the 30-day window that we're interested in for our time at risk. Where you will implement this and create analysis specification, you'll look for this time at risk parameter. And I'll note that you can define multiple time at risk. So you can have multiple study designs and run them really nicely and easily by just creating multiple of these values. So you can see here I'm doing 2 different time at risk, which are actually exactly identical in this case, but you would change them probably. So you can give a name to it. Is it on treatment? Is it intent to treat? Is it something else? You can give it that label. And then you have the risk window start, which is the adjustment from the start anchor. You name the start anchor. You have the risk window end, which is the adjustment from the end anchor. And you have the end anchor. And so these kind of columns then correspond to analyses, and you can have as many of these as you would like. And this is where you would define them. We spoke also about the outcome look back window and the cohort clean window. And so again, this is the time if you have, heart attack, you'll have many, many different codes for referring to the same heart attack. So how much time are we going to wait before we say, okay, this is now a new heart attack? And so maybe for a heart attack, it will be a year. Maybe for something like a cold, it would be less, like 30 days. That's up to you. And then another choice that we might make is, are we interested in patients that are experiencing this outcome for the first time ever in their whole life? Or is it enough for them to have not experienced it within that standard clean window that we've defined? And so you can see down here where it says, alternatively, we could remove anyone who has had the outcome at any time prior. And now we're kind of overriding the clean window. We're just looking back for the entire history in terms of the prior occurrence of this outcome. In Strategus, in this file, we have this outcomes parameter, which is at the top. And so, as we've kind of mentioned, you can run one study and look at multiple outcomes. So this could be a list of very many different outcomes, AMI, angioedema, the list could go on. And for each outcome, you can have a different clean window. And you can imagine that that makes sense depending on the clinical context. So in this case, it's 365 days for both. You might adjust that depending on what the outcome is, and that's where you would do it. And then if you look a little bit further down in the script, we have this parameter, use clean window for prior outcome look back. And so this can be either true or false. If it is true, we'll use whatever the clean window is and only consider removing patients who have had that outcome within that clean window. If this parameter is set to false, then we're looking at all time prior, and meaning that we're only going to include outcomes that are experienced for the first time in the patient's history ever. Okay, so those are kind of like the timing sort of considerations. We've talked about propensity score and how we'll use large-scale propensity score. And Linying mentioned that there are multiple different ways that we can use the propensity score. Matching is what we'll do commonly. And as was mentioned, we might do this one-to-one matching. We might do 1 to n, especially if we have different sample sizes. That might be really helpful. We also can do stratification, where we kind of bucket the propensity score, I think it's by 10, right, into 10 buckets. And we can also do weighting, where we'll now keep everyone but weight the population according to the propensity score to get that balance. We've talked a little bit about this as well, which variables go into the propensity score model. Traditionally, we would have experts come up with this list of 20 that George is saying that may or may not ultimately get matched on. There's also another approach that's this high dimensional propensity score, where you rank very many variables and then you pick some certain threshold. And I think this is found to be kind of unstable, and that it's much better to use large scale propensity score, where we're using everything and where it's really data driven, and we'll know that the chances of achieving balance are a lot higher. And we also noted that there are these concepts to exclude, which is most explicitly, we need to exclude the target and the comparator. And so this is the thing that very consciously and actively we'll have to do in our code. And then again, we must think, are there other examples like this injection device or these other kind of outlier or, edge cases where we might also need to exclude those concepts. We kind of talk through this, but we know which concepts to remove. We have kind of these standard lists, and there are these other data-driven approaches that will be highlighted in our diagnostics. So there's not so much that needs to be done in this case. Okay, where do we actually do this in our code? So we have this parameter, TCIS, that stands for Target Comparator Indications, meaning that you could have multiple specified in this list. So you'll ultimately set your target ID, your comparator ID, your indication ID, the cohort IDs that correspond for each of these. And a little bit further down in the set, you'll see excluded covariate concept IDs. And so here I have 2. I switched to diuretic apparently, but you can put that back as ARBs. And so these are the covariate concepts IDs that correspond to the exposure and comparator drugs. I'll note that by default, we're only including the top level covariate, and all the descendants are automatically included. So you don't need to list all of the descendants explicitly. There are also these propensity score settings that usually don't need to be adjusted, like the max cohort size for fitting, but it might be relevant, so I'll highlight it. These are kind of parameters related to the propensity score. Usually these don't need to be changed. For the outcome model, we have a few different choices depending on what it is that we're trying to evaluate. You could do a logistic model where really you're just asking whether or not the outcome occurred as a binary, yes or no. A Poisson model would be the number of times that the outcome occurs. And Cox is what we use most commonly, which is kind of the time to event. Usually, as I said, we used the Cox, and so the Cox model, and so usually this isn't changed, but I'll note that in this fit outcome model args parameter, which is in the create analysis specification script, you can change this model type to be one of those other models if that's relevant. Okay, the last thing I'll mention is that there also are some parameters that you might wish to adjust that are just for some further data refinement. For example, it might be relevant to use only valid gender concept IDs. And so you can set, these are the concept IDs for male and female respectively, in which case you're removing patients who have an unknown concept ID that might be important for the covariate matching or for something else. You might also want to set a minimum and maximum age. Maybe that's 0 and 120 or something, or maybe it's something else. Maybe your minimum age is 18 or something like that. So if you want to do some data refinement, that can be done in the analysis specification. It does not necessarily need to be done in the cohort. And so this is where you kind of have some flexibility. It could be built into your cohort definitions, or you could do it here. There's this one other data cleaning element where you can set the start and end dates of your study kind of within your database. So if you know that something wonky has happened in your database, or maybe it's COVID, maybe you've changed data platforms or something like that, and therefore you want to scope the study period you're looking at, you can set the study start and end dates here. And so that's just kind of a data cleaning thing. We've kept mentioning and skipping over self-controlled case series, and we'll do that one more time. I'll just mention that there's this alternative study design of self-controlled case series where really you're comparing a patient to themselves in the time periods where they have the exposure and when they don't have the exposure. And I'll note that we can compare many different chunks. Maybe a patient takes a drug, they go off the drug, they come back on the drug. We can look at that. We might look only at certain chunks of time when they go on it for the first time. But you're comparing the patient to themselves and whether the outcome is occurring during the time they are exposed or not exposed. And so this is the no-use comparator kind of alternative study design that we just want you to know exists, but we won't go into too much depth in. Okay, then we mentioned that after we've generated our JSON file, now we've run it, now we'll get this our Schuemie app that we can look into for our diagnostics. And so we'll spend a little bit of time looking at the diagnostics and how they're helpful in us interpreting our results. So the first diagnostic that we have is equipoise, and equipoise uses the propensity score and helps us determine whether two cohorts are similar enough to be compared. The threshold that we use is that we want an equipoise value that is greater than 0.5. What that means is that more than half of the cohorts in each group have a preference score between 0.3 and 0.7. That means that they are, if their preference score is 0.9, it means like they're really likely to get that treatment. And so we want cohorts that are a little bit more comparable, where they could have gone in either treatment group. And so that helps us know that our estimates are a little bit more reliable, because it's not the patients aren't coming from totally different data distributions. So this is kind of the threshold that we use. Maybe looking at this picture, what do we think? Does this pass the diagnostic? Do we feel like the kind of shared region between 0.3 and 0.7 is greater than 0.5? Maybe we can show hands. Yes, no. Yeah, yes. Is that I see some in the middle, and I think that's probably right. It looks maybe a little close to 0.5, maybe hard to tell. But we would get some number from corresponding to this graph, and we would be able to know for sure. So what do we think about this one? Does this pass our diagnostic? Yeah, that looks great. Yeah, so this, it means that even though we have like so many patients in our data set, we can see that the majority of both of these cohorts and these samples fall between this 0.3 and this 0.7, meaning that we can't, based on the covariates alone, perfectly discriminate between which patients are going to receive which drug. So that's a good sign for us. What about over here? How are we doing? Bad. Yeah, this is bad equipoise. And so that it means that there's something about the baseline covariates of these patients that's pretty strongly correlated with which drug they're getting. So it means that these are really not comparable cohorts, and maybe there's something else we need to do. Maybe we need to look at some different subpopulation or something else. Yeah, question?
The reference score is the same as the propensity?
Yes, yeah, it's the same. Okay. Is it not the same? It's basically the same. Yeah, it's an.
It just divides in case the prevalence of the two groups is not equal.
It's standardized, yeah.
That's all. It's normalized for the prevalence different than prevalence between the two groups.
Okay,
But conceptually, it's like yeah.
Okay.
Yeah, it's,
So that the two areas look the same size instead of one of them being tiny and one being huge.
yeah. Okay, great. So this was our first diagnostic. Our second diagnostic, I think it gets to a question that was being asked earlier about covariant balance. So propensity score kind of collapses all the covariates. And so now we actually do care a lot about the individual covariates and making sure those are balanced. And so this diagnostic, we compare the standardized mean of each covariate value between the two cohorts. And so this graph you can see on the x-axis, it shows the difference before matching. And on the y-axis, it shows the standardized difference after matching. And so the threshold that we kind of want is we want all of these, and each blue dot represents one covariate, I should say. We want all of the blue dots to be below that red line, below the 0.1 difference after matching. So that tells us that even if the propensity score is matched, we want to make sure that each covariate is also being matched really well. And so we're assessing all of the however many 50,000 or whatever covariates that are being included. It says that if we have too large of a difference after adjustment, it might mean that we have some residual bias. So that's why this diagnostic is helpful. Okay, so let's look at this one. How do we think? How is this diagnostic? Is it good? It's good. Yeah, this is a good example. So it means that you can see the 0.1 line. There's no red this time, but you can kind of see that 0.1 line, and all of the blue dots are below that value. So that tells us that after matching, even though we have some dots that before matching were pretty different, after matching, all of them have not much of a difference. So that's a good sign for us. How are we doing over here? Is this a good score? No, this is a bad score. Yeah, so you can see that we have a lot of covariates, individual covariates that even after propensity score matching are pretty dissimilar. And so that is kind of an indication to us that we have not sufficiently matched each of these covariates, and therefore maybe we have some residual bias. And so in this case, this diagnostic would fail, and we would not, maybe consider the results. Yeah. Yeah, that's a great question. So yeah. The way that we, and fact check me if I'm wrong, the way that we do this is that if any one of these diagnostics fails, then we don't unblind the results. And so we actually say for good science and, to avoid, bias and p-hacking and all these kinds of things, we won't even look at the result to the true value because there's too much residual bias for it to be fair. So in this case, these methods, we have to do something else. We have to do, so George said we do a randomized controlled trial, or maybe there's something else about the study design that we can do. Maybe there's like another method that we need to try. Maybe it's like mediation analysis. I don't know. Something else entirely would need to be done, but this approach wouldn't address all of the bias is what that means. It means we have to do something else. Yeah.
So at what threshold would you make that call? Because I guess what if some of these aren't actually confounders? It doesn't matter if they're above 0.1 because they're not going to influence the outcome. Is there sort of like a review stage of what these variables are, or how much constitutes like big violation?
Yeah, that's a good question. I don't think right now we have that implemented. We make sure our threshold is that we make sure that all of the covariates don't have a difference, that it's below this 0.1 threshold. And so right now I don't think we do any subsequent analysis, but I don't know if we could or if we.
The step before this, when we were generating the propensity score, we got an error report saying that this variable is correlated more than 0.5, in which case we had the opportunity to say, is this thing by domain knowledge known to be an instrument? And that would be the example of the injection for GLP-1s, and you'd say, yeah, that's kind of an instrument. I can't imagine an injection causing the outcomes. I know that it's associated with just one of the drugs. So you had the opportunity there. By the time we get here, you read the papers, and it's always like they adjusted for 20 variables, and 2 of them didn't reach. I picked the 20 confounders out of 60,000 variables. Then I run the study, and 2 of them aren't balanced. And then I argue, well, they're not confounders anyway. Well, why'd you put them in the 20 in the first place if they're not confounders? We only picked 20, and you couldn't even get those 20. So we actually don't look at the results. So we see the diagnostics. We know which variable is bad. I mean, we could, in theory, since we haven't looked at the results, we don't know if it's giving an answer we like or dislike yet. That's why we blind the results. We could, in theory, look at what dot is above 0.1 and get rid of it because it's an instrument. But you don't want to get rid of it because you don't think it's a confounder. You want to get rid of it because you know it to be an instrument. In other words, you need strong evidence. It shouldn't just be, it's probably okay. It should be, oh yeah, I know that's an instrument because GLP-1s are only given by injection. Of course, that makes sense. versus, you know, it's, you know, their blood pressure. Well, I'm sure blood pressure doesn't affect their angioedema, so don't worry about it.
But then they're like, especially when your cohorts are big enough, like you have thousands, and you're starting to compare it, this typically doesn't happen.
Okay.
In this case, this I can already tell by how this is. These are very small cohorts, and hopefully with the new balance metric that we just published about, that hopefully will be available soon, this will also not be a problem with smaller cohorts.
What?
Yeah, it might just make
Yeah.
it easy, because remember, even with our algorithm, we're never over 0.25, which we like because Austin's other threshold is 0.25. And we argued that
Yeah, but
even with the correction, we never get to 0.25.
we don't-
This is 0.2, yeah.
0.2, so we
Yeah.
Yeah,
How
but
small are those cohorts? Are they?
I think we're
I don't know.
If they're like 100, then yeah, it might actually pass.
the lines tell you that we're discrete values, which means. that-
Oh, yeah, that's true, yeah. Yeah, that's small. Okay, so it might, this might pass our new algorithm.
For small samples.
Yeah.
For small.
Yeah. There was another question? Or no?
My question and comment, I guess, even in terms of like going forward, would this be also an opportunity to do a sensitivity analysis? So if we look at sort of the ones that are far in distance, them, would you sort of continue the experiment with the balanced one going forward, and then alternatively with the selection of some of the very distant various people, if they make sense?
It's a good question. I don't know what George thinks. George is thinking.
You know, because the problem, the two things you're comparing are not balancing it and balancing it incompletely. So the sensitivity, so, you know, it's good news if you don't see a difference in the outcome. But remember, you're not comparing balancing to not balancing, you're comparing poorly balancing to not balancing at all. And the fact they don't see a shift between poor and none, does that mean that I wouldn't see a shift if I got to good balancing, which I never have an example of that. So as a sensitivity analysis, I'm a little nervous. But certainly, you know, I mean, that's the problem is you start p-hacking.
Well,
after a while, so
I'm
I'm
going
worried
to
about
the outcome, it's exactly what you said, which is just staying at the, is it the distance of these relative to the exposure, like not looking at the outcome. So you continue, like, it's, you know, we threw it in, this is what we hypothesized based on whatever, all the variables are still in, and we run the analysis, but then at this point where we're like, scenario 2 is, we see that there's some, you know, there's some of these variables that are far apart, and then we remove them because just, in this case, it's
So
just.
we removed
statistical.
it, but then we would look at the result, presumably.
Yeah, then you continue through a second scenario, which is, it was removed at that point, and then the analysis continued. But it's still, you're still blinded to
Well, it
the
means that
outcome.
you might have unmeasured confound, like it's suspicious
Mhm.
confounding them. You just made something that you're adjusting for unmeasured
Mm-hmm.
in the analysis, and you don't know that it's connected to the outcome, but if you don't know that it's not connected to the
Right.
outcome, it could be, but then you could.
It could be performing as colliders. I mean, there are lots of, I mean, with so many variables, I think.
Yeah, I don't know.
Yeah, I know that we're spoiled. Like in my company, we have multiple databases, and we run it across some single study across multiple databases, and then some drop out, and we just that's it. We stop with them, and we continue with the ones that remain. It is fair game if you encounter this, you say, well, maybe I need a different like analysis approach. Like if I were using events for stratification, then this might be the point where I say, okay, I will be matching instead. That's fair game because you have to get a look at the outcome.
You're still slightly impacted, but not as bad. You know, yeah, no, outcome because it's still a stepwise procedure until you get a diagnostic. You're like, that's still a multiplicity.
Yeah.
You can't put your finger on the scale of the right one, but I don't have to think about it. Not at all.
So there's in the extreme there.
May I have one more comment?
Sure.
Sorry, just have to come on time. Yeah, I'm just saying, for the shared code is 1.1, maybe this is makes sense for the big database, the huge, right? Because you know it's the same database, it's big, sample size, this makes sense. Maybe that's
Yeah.
Two things on that. So one is this paper we mentioned is increasing the threshold for small samples. So it's doing exactly what you're suggesting. So it does the adjustment based on the sample size. It does the calculation for that.
And it goes up to what, George?
But it stays
0.25. Yeah.
Because I looked at it. The reason it sizes, so it brings it up, but it doesn't bring it beyond 0.25. The other thing is, you know, you're describing a special case where you're comparing things from two different data sets and trying to get them to balance, which must be, like, I don't have experience with it, but I imagine it must be hard to get those things to balance.
Okay.
This is just one of the diagnostics. So later on, Martijn will talk about negative controls. So that is another way to assess, right? Does these imbalance cause any residual confounding if you look at the negative control outcome? So currently, our implementation, the pipeline is taking this in a more conservative way. If the database fail any of those diagnostics, we would not include that database in our meta-analysis. But I guess in the future, we could look into more, I don't know, for example, how many times a database failed the covariant balance diagnostic but passed the negative control, right? And if that gives us a more holistic view of the right, how serious really is this one covariant that exceeds 0.1 standardized.
Yeah, that's a great point. So that's a perfect transition to move on to the third diagnostic, which is expected absolute systematic error. And so this is really, as Linying was saying, this is a measure of residual bias that might exist even after the propensity score analysis. And we estimate this using negative controls, which Martijn will talk a little bit more about later. But basically what we do is we have this list of negative controls that we practiced with earlier, ingrown toenail, things like this, that we would not expect to be caused in either direction by the caused or prevented by both the treatment and the comparator groups. And so then we look to see if there is a statistically significant association for these negative controls. If there is, then that point would show up in these orange regions, and that would push the score higher, and it means that, okay, the negative control is showing up as a false positive, meaning that there's probably some residual bias. So what we want is for all of the points, the blue dots, to appear kind of within this V, outside of those triangles, meaning that there's not a statistically significant association, and so it's a showing up negative as we kind of would expect. And so in this case, you can kind of see both in the uncalibrated and calibrated versions. And so in the calibrated version, we kind of do some adjustment to kind of make the negative controls appear as we would expect it. But in the uncalibrated and calibrated versions, you see that all of the points are within the red V. And so then we have these low E scores. You can see 0.1. So that low E scores is good. There's little residual bias is what that means. And here you can see on the bottom, we have this uncalibrated version. There are a lot of these negative controls that are appearing significant. And so the E-score is higher, it's 0.82. And so that tells us that maybe we have some residual bias. So once we've calibrated the results, you can notice in the higher one that the points are within the V. Okay, and the last diagnostic that we use is minimum detectable relative risk, MDRR. When we're kind of setting out to start a study, normally we do some kind of power analysis to see how many samples do we need to show the effect that we're expecting. With observational data, our N is already defined. We can't change the number of patients that we have or subjects that we have. So instead, we use this diagnostics to help us understand, given our sample size, how strong of an effect is it possible for us to detect. And so you can see here with the MDRR, the lower values are better. And so all databases have an MDRR below 1.75. An MDRR of 1.75 means that we have the ability to detect a 75% increased risk if that's apparent. And so here, the majority of these databases have a value that's actually lower than 1.1, which means we have the ability to detect a smaller risk, a 10% increased risk. So where our sample size is large enough to be more sensitive to smaller changes. By contrast, in this study, these MDRR values are really, really big. They're a lot greater than 6, which means we would only have sufficient sample to detect a 600% increased risk or more. So we're really underpowered to detect what is very likely to be a much smaller increase of risk. And so we want lower values for this. So this is actually my last slide and am I passing it on to Martijn now on negative controls? Yeah, okay, perfect.
All right, so I will be talking about meta-analysis and negative controls. And so I'll be going until 4, and then we'll have Linying with a cool interactive session. So meta-analysis, so why do we even care about meta-analysis? Well, in Odyssey, we like to think of research being done across a distributed research network. So typically we have multiple sites that have data, hospital EHRs or administrative claims data. And what typically is the case is that we cannot actually share patient-level data. So any approach that will require us to pool all the data in one place, that just doesn't work. But that doesn't really bother us because we can still do our analysis. It is important that each site uses the OMOP common data model, obviously. So the data sits within the firewall of these organizations in the common data model. And then any site could decide to lead a study. They would develop the analysis locally. And as Tara was showing you, we can actually use a Strategus package to create specifications that define the analysis. So you can do that locally, and the software is designed so that you can then share those specifications with other sites. So we send it over to them. They then can run it locally and produce aggregate statistics like hazard ratios and patient counts and things like that. And because they're aggregates, those are things that we can share between sites. They're not patient-level data. And then we send them back, and then we need to combine them in some way. And this is where the meta-analysis comes in, because now we have these aggregate statistics, and we have to basically probably want to have a single answer, like does this drug compared to this other drug cause this outcome? And so we can use traditional meta-analysis techniques, like you might be familiar with Dursimonian and Laird or any other random effects model. One thing that we have observed is that those can actually be problematic because of when counts are small or 0, and this is outcome counts. So you can have 100,000 patients on the drug, but then you could still have like 2 or 3 people that have the outcome while on the drug. And so in that case, it could actually be that those traditional meta-analysis techniques that you might be familiar with actually produce biased results. And I won't go into the math here. We figured that it would be too much. But I just wanted to point out that we actually have thought about that in Odyssey, and we've developed this new technique called likelihood profiling, where it's not just the hazard ratio and its confidence interval that we're sharing, but we're actually sharing the full likelihood curve of a database. We aggregate those, and then we can still do a meta-analysis, but now we are not harmed by any bias caused by these small counts. And just to illustrate this, and then I'll move on. Here you see on the left, if you were to use a traditional meta-analysis technique, like the vanilla ones that you know maybe in the meta-R package, where some of the sites have 0 counts, so they drop out. Other sites have low counts, so they're actually the likelihood distribution is skewed, but we ignore that in the traditional meta-analysis. And now at the bottom, you see that we get a summary estimate that includes the null, so we're not rejecting the null. And on the right-hand side, this is the likelihood profile approach that we use in Odyssey, where we recognize that the likelihood might be skewed, so not normal, and we also recognize that even if there's a 0 count, we actually are still learning something from a site. And then if you combine the information that way, so the exact same data, but now not requiring the normality assumption that's on the left-hand side, you actually get a very different answer, the right answer, which is very different from the one that you would get from the traditional meta-analysis. Just to tell you that that's integrated in all of our tools. Like the Strategus tools automatically do this for you. They produce the likelihood profiles, and when you call on evidence synthesis, it actually will perform the meta-analysis in this specific way. Any questions about meta-analysis before I move on? Nope. All right. Excellent. Then a little bit on negative controls. We already talked a little bit about them. What is a negative control? It's basically an exposure outcome pair where we know a priori that there is no causal relationship. We typically define a negative control relative to a causal question of interest. So we might be interested in whether like, ACEs compared to ARBs cause MI, and then we want a negative control that's either another exposure that we know doesn't cause MI, but we tend to use negative control outcomes. So these are things that we know are not caused by our target or our comparator exposure. I kind of like this specific example from this quite old paper now where that explains the use of negative control. So in this case, the authors of this paper, they were exploring whether infectious mononucleosis, rubella, or measles as childhood diseases had any relationship with multiple sclerosis. And so they ran their analysis, and sure enough, for all three of these diseases, that they found a significant increase in the risk if you had those diseases. But they were very uncertain about the method that they were using, and so they also included these basically prior exposures or prior things that they thought could never have a true causal relationship with multiple sclerosis, so a broken arm, concussion, and tonsillectomy. And sure enough, for two of those three, they also found a significant association for concussion and tonsillectomy. And so that led them to believe, well, there must be some sort of a bias going on because we don't believe that there actually is a causal relationship. The next step that they then did I find very shady, which is they said, well, in the negative controls, we observe anything up to a 1.25, so we can sort of explain rubella and measles away, but surely it could never explain away infectious mononucleosis. And you might remember that that's actually the title of their slide. It's saying mononucleosis causes multiple sclerosis. And I think that's a little bit odd because maybe then the fourth negative control that they had included also would show an effect of 2.2. So if you have only a handful of negative controls, it's actually hard to draw conclusions from that. For those of you who are familiar with the negative control literature, know that oftentimes people also have an additional requirement. So it's not just that there is no causal relationship for your negative control, but they also require that it has the same unmeasured confounding as your question of interest. And I agree that that's something that you ideally would want, but I think there are some problems with that requirement. One is that I don't actually think we know what the true confounding structure is. And I find it hard that to believe that people can draw these giant DAGs with causal relationships, and they were sure about everything except the question that we're asking. So why were you not sure about the question that you're asking then if you were so sure about everything else? And actually, we find that any two experts will disagree on what the confounding structure is and are likely to miss important confounders. We actually have a nice paper that looked into that. Also, if you think, well, why don't I just ask the data what the confounders are, which is also something people recommend, that would be nice, but typically we don't have the data for that. Usually the number of people that have the exposure, there are many of those, so we can fit. That's why we can fit a nice propensity model. But the people that have the outcome in our analysis, usually that's like tens, maybe 100, but that's not enough to evaluate for every variable whether or not it's a confounder. Also, if you did know the confounding structure, well, you're asking for basically a unicorn. It's something that has the exact same confounding structure, but not the causal relationship, so it's very likely that such a negative control doesn't exist. So instead, the Odyssey approach is that we don't care about the confounding structure. We just wanted to not have a causal relationship. That then makes it very easy to find negative controls. We actually have a tool that we created that just automatically generates candidates for which we know that there is no evidence in published literature, in product labels, and in spontaneous reporting that there is a relationship. So we're fairly sure that there is no real relationship, and we just rank order by prevalence, and then we just do the game that we did earlier, where we just ask, is this a negative control? Yes, is this negative control? Well, maybe not. This is negative control. We just go down the list until we have a sample of negative controls. The important thing, I think, is if you want to avoid investigator bias, you should pre-specify the negative controls, so not change them after you've seen the actual results. And also, as you'll see in all of our plots where we show negative controls, we don't show you what the names are, because otherwise you see the one negative control that's all the way out there, and then you look at it, and then you start making up stories that explains it away, and then you're going to take it away. And that is basically p-hacking. So what can you do with a set of negative controls where we don't know the confounding? Well, you can just plot them like here, and Tara already showed you similar plots. So on the x-axis is the effect size that was observed using our method for a negative control, and on the y-axis is the standard error. And so the higher you go, the wider your confidence interval is. In this case, we're just looking at one-sided p-values, and anything below this dashed line is statistically significant. And remember, these are all negative controls, so there is no causal relationship. I'm showing you one method on the left that has all of these negative controls shifted to the right. So for 34%, we are rejecting the null, even though the null is true. That is the definition of a negative control. And for the method on the right, we see that, just as Tara also explained, they're all nicely within this funnel, so we actually, it's not saying that any of these negative controls are actually 1.5% is declared to be statistically significant. And so if you see something like this, well, which method would you trust more? The one that says that 34% of negative controls are actually, there's an effect, or the one that doesn't show an effect for the negative controls? I think the intuition is fairly straightforward, that you don't want the left method, you want the right method. We can actually quantify that. The problem is any one of these negative controls themselves has some uncertainty as expressed in a confidence interval, but we can combine them together and fit what we call a systematic error distribution. So that's shown on the bottom is a distribution that's basically fitted based on the dots above, taking into account their uncertainty. And this sort of summarizes what we already see in the data, that the left method is shifted to the right. So the mean is shifted to the right, but also there's just more spread. The right method, it's not shifted in any direction, and there's not that much spread of these negative controls relative to the random error that was there. We can summarize this in something that Tara already mentioned, the expected absolute systematic error, or EASE. And this then forms the basis for another diagnostic that we have. So in this case, the one on the left-hand side had an E score of 0.49, and the one on the right, an E score of 0.04. And we just have a threshold. If it's greater than 0.25, we say it's out. So just like for the balance, we had a yes, no, a go, no-go decision based on a diagnostic. Here we have the same based on these negative controls. In addition, we can also, for the ones that you then keep, we can say, well, there's still some systematic error shown in this distribution, so we could actually calibrate our p-values and confidence intervals and max SPRT values if you're doing sequential analysis. And Tara also showed this plot, but just to show it again, so here the blue dots are all the negative controls. Anything that falls below the dashed line is statistically significant using the traditional p-value. And then what the p-value calibration does based on these negative controls is it defines this orange area, and only things in that orange area are statistically significant using the calibrated p-value. And this is a very extreme case where the negative controls are really far apart. It's probably case control design, but that's a whole other story. This is not usually what they look like for us. Like if you use large-scale propensity scores, it doesn't look anything like this. But you can sort of see the intuition of what the method is doing is only if you have an estimate that's outside of the range that is observed for the negative controls, should we be rejecting the null, because the negative controls are the ones where we know that the null is true. So it's implementing this intuition in a statistical framework. So in summary, When combining evidence across a distributed network of databases, we use meta-analysis to avoid having to share patient-level data, and we have this fancy method in OHDSI for avoiding bias related to small counts. And we use a distributional approach to negative controls using many controls with unknown confounding. I would say one of the biggest advantages of this approach to negative controls versus the one where you want to find the perfect one is that it's very practical. And as a consequence, every OHDSI study uses negative controls and uses them as a diagnostic. It's sometimes just mentioned as 1 or 2 words in our papers, but we still do it every time, whereas practically nobody else uses negative controls, just because if you really are going to hunt for the perfect negative control, you're probably not going to find it. So I'd rather have our approach that you can always run, and we believe it's a good approach, than the approach that really nobody uses because it's too hard. And so we use these negative controls both as a diagnostic, so based on the E-score, and as for subsequent calibration. And with that, I will hand it over to you.
All right, you have made this far. Good job. And the upcoming one, I think, is the most fun and most cool part of this tutorial. If you feel lost or overwhelmed by everything that you have learned so far in the past 3 hours, just so you know, this is totally expected, totally common. I spent 5 years of solid PhD work in learning causal inference, all these analytics and how to do it. And we packed that into a 4-hour tutorial. And you get the gist, the overview of everything that we have made available as open source softwares in the OHDSI community. But so I would acknowledge it is a lot of things to understand in order to design a good study. But actually, once you know what are your phenotypes, your target cohort, and you figure out all those questions, the OHDSI codes analytics have done 99.9% of the implementation for you. So what I'm going to show you in the next an hour-ish is to show you that for everything that we have described so far, building phenotypes, building cohorts, running large-scale propensity scores, 60,000 covariates, running these 4 or 5 different diagnostics, all of that can be done within less than, I would say, 50 lines of codes that you need to change in our study template. So that is my goal. And we'll know but in an hour whether I achieve that or not. So first thing first, OHDSI use mainly R, the programming language R, and the web API RStudio to do most of our coding. So we have prepared this setup instructions that is linked here. I also share the screenshot on the slide that will walk you through, depends on whether you're a Windows user or Mac user, where you can download R and which version, and RTools, RStudio, Java, and how to set up a GitHub token so that you can install many of the packages that we made available on GitHub. So if I click here, so you will get these slides, and the links are all there, and you can try that out when you are back home or when you need to design a study. So for now, we only have an hour for this part. I think it's better if you let me walk you through it. Otherwise, we'll get distracted very quickly and get lost. So this is the web page, and we. Yeah, I need to exit the full screen. Thanks. From here. Yep. So this is the instructions that will walk you through how to set up the R environment. And as a piece of device, I highly recommend you to install exactly the R version that is specified here, up to the 3rd digit. That's 4.4.1. That will save you from a lot of the bugs and troubles later on. So it is better just to follow this instruction very closely. And then the rest should be straightforward, and we include all the links and the screenshots that to show you how to do this step by step. All right. So now let me go back to. Yeah, and I've put, because now I think R is at 4.5 point something. So this is a slightly older version. I think it was released maybe a year ago-ish. And I include links here where I find you can download this exact version from an archive. Okay, and for today's, so we have study templates that are GitHub repositories on the OHDSI website, GitHub website, and maybe let me. So this is, I call this official one. So you see it hosted in the OHDSI studies account. It's very similar to the one that I will show today, maybe different by a few packages versions. So if you have and this is the one I believe we included in the email we sent out to all of you prior to the symposium. So if you have downloaded this, you can do it in several ways. The easiest one would be to click this code button and download as a zip file. And this includes all the files that you will need to run an OHDSI network study. Some of that, for example, download cohorts, creates analysis specifications, and Strategus code to run that Tara has mentioned previously in her talk. So let me do a quick survey by showing of hands. How many of you have downloaded this GitHub repo onto your local laptop? Great. I see. So it's about a third of the attendees here. For those of you who haven't, let's try it, I would say. George, Martijn? I think we'll have enough time for you to, it'll be more fun if we can actually open the file and follow me to, change some cohort IDs and specify a database schema. So this is the tutorials that I prepared. Is maybe slightly different, but so if you're downloading right now, I recommend you download this one. The address is at, let me make this bigger. GitHub.com, Causal AI Lab, and then /PLE tutorial OHDSI 2025. If you type that into your browser, then it should bring you to this page. The default branch is developer, and this is the one that you want to download from. All right, so you click code, download zip. I'm also going to do it here. Yeah, once you download the zip file, you just unzip it, and you should be able to see everything now on your local laptop, all these files here. So what is important? So this is an R project. It is kind of a self-contained environment with codes and also packages and versions and everything pre-specified. If you're used to just click random like a R script and start it, don't do it here. Always make sure that you click the R proj. Is at the top? Yeah. So it looks something like this. I can make it bigger, showing the icon. So make sure you're clicking this .rproj to open this project. Great, so it's now showing my screen. This project is open in RStudio. You will see, it will tell you what version of R you have. And given this is Martijn's laptop, it's at 4.4.1. Yeah, and it has some other auto-generated scripts. You don't need to worry about that. The next thing you want to do when you open an Odyssey R project, don't do it here because you will never be able to finish even just downloading all the packages with this hotel Wi-Fi. But in reality, rinf, right? That's comma. So rinf is a R package for managing R environments. And then you type in restore. So by the way, all these commands are in my slides, so you don't need to worry about it. You can take screenshots if you want, but yeah. So yeah. For now, I will. Can I type enter and just to show how it works? So if you type this, it means I want to restore all the R packages that have been pre-specified installed in this R project. And usually if you're a data partner, meaning someone else designed a study and you want to run the study on your database, running this will ensure that you create this exact same R environment, more or less, as the study lead. Right, so if I click enter, that will tell you, well, do you want to proceed, right? Do you want to install all these packages into this environment? So you click yes, and it will start installing. So usually this will take somewhere between 10 minutes to half an hour, but with the Wi-Fi here, it will probably take much longer. So if you haven't done this prior to come here, don't worry, you won't need this environment to run to follow the rest of the tutorial. All right, so oh yeah, and Martijn apparently have installed everything, so this only takes 30 seconds, and then we have the environment ready. Okay, so for the next part, I wanna show you how we can create the cohorts using Atlas. So let me go back to the slides. All right, so here, these are the templates. I open the rproj and then run the restore command to install all the packages. So next, let's create the target and comparator cohorts. My motivating example is the GLP-1 receptor agonists. So sorry to switch minds between hypertension and diabetes a few times today. So we're back to the diabetes world. And remember, our target cohort are people who are exposed to GLP-1s. It's a class of drugs. So that means we want to identify people who are exposed to GLP-1 receptor agonists. And we, imagine the study lead tell you, okay, we need to limit to the earliest exposure per person because we want to study new users of a drug rather than someone who have been on a drug for a long time. We need to specify observation window that's 365 days before their treatment start date. This is to ensure that we have observed this patient long enough to capture some confounders. And then there's a bunch of inclusion criteria. Specifically, adult patients have type 2 diabetes prior to their index state, no type 1 diabetes, no condition occurrence of secondary diabetes mellitus, no prior exposure to the alternative anti-diabetic meds like DPP-4, and so on and so forth, and no prior exposure to other anti-diabetic that does not belong to any of these 4 classes. And then maybe you want to specify to have prior metformin use and no prior insulin use, and so on and so forth. So how can we create this cohort using Atlas? And I will walk you through this on the screen here. The if you have an atlas at your own institution, then you can use that. But if you don't, then there's an atlas that's publicly available for everyone, and this is the address. So I will take you there. Maybe I have it here. Okay, so.
You can close the download thing on the right, maybe?
Yeah. So if you go to atlas-demo.odyssey.org, oops. Then this is, you'll see a website that looks like this. And if you click cohort definitions, and I think we click the new and there's a button, I think in the upper right corner called new cohort. This is the screen that you will see. So this is a blank template that includes nothing. So you will give it a name. For example, let's say I call this, if you don't want to know, because this is a public atlas, if you don't want people to know that this is your cohort, you put some other identifiers that's other than your name. I'm okay with that, so I will use that, my names. That way it'd be easier for me to find it. All right, and I will call it GLP-1 receptor agonist. I click Save. All right, so I've created an empty cohort. I name it GLP-1 receptor agonists. Next, I will enter the cohort entry event. In this case, right, if this is my target cohort, that means I want to find the people who are exposed to GLP-1 receptor agonists. What I did prepare beforehand, or I didn't show you here, is to how to create the concept sets to find the RX norm, like the STOMAT IDs that corresponds to GLP-1 receptor agonists. So it's like the phenotyping, as I've done that beforehand. And if I have that concept set for this drug class, then because it's a drug, right? So so first you need to decide what is the domain that defines your cohort entry event. Is it exposure to a drug or is this a condition? Oftentimes in PLE studies, the cohort entry event is exposure to a drug. And what that means is that when I add the initial event, see, I need to select from, can I make this bigger? Yeah, cool. And this is better. I need to select from these lists down here. And what I'll select is add drug exposure. Right, so I click this. And then, so it says events having any of the following criteria, a drug exposure of what? Right, it's not any drug, it has to be a GLP-1 drug. So if you click this arrow, you'll see import concept set. So this is where now I can import my concept set that correspond to GLP-1. And hopefully it will show up in a few seconds, great. And for all the concept sets that I created for this tutorial, I create under this key PLE25. So see, these are all the concept sets that we're gonna use in this, creating this cohort. But for this one, I need to find my GLP-1 receptor agonists. Right, so I click this, and it's now my cohort entry event here shows a drug exposure of GLP-1 receptor agonists. Just to show you what this concept set includes, so if you go to concept sets, this tab, you will see now I have a concept set here. And if I click it, you will see that it includes actually 6 concepts that correspond to semaglutide and all these other drugs named that I don't know how to pronounce. And we select all the descendants of this concept and all its descendants. So even though we only include the 6 here, the actual number of concepts that are being included is 1,397 concepts that are the more specific, with different formulation, dosage, and these are all OMOP standard concepts. So, all right, so let me go then back to definitions. Then we'll add some initial events. Remember, first I said we will limit to the earliest exposure and also people with continuous observation of 365 days. So this is where you select, do you want the earliest exposure or all exposure or the latest exposure? So here, earliest is what we want. And for the continuous exposure window, we want 365 days. So we put 365 days before and 0 days after event index date. So that means we capture the 365 days right before the treatment start. All right, and we have several restrictions. First, we only want to include adults, people whose age is 18 and older. So that means I clicked here, which, so age is a demographic. Right? So we want to add a demographic, and here we want to add an age criteria with age greater or equal to 18. Then we also want people with, what are the others? Having type 2 diabetes prior to index date. Right, so that means for each of the inclusion criteria here, it will be a set of things that we enter. So if I click new inclusion criteria, I can call this, so let's say, having type 2 diabetes. So, right, the cohort entry event just find everyone who's exposed to GLP-1 receptor agonists and whose age is more than 18. But that's not good enough, right? We need people who have type 2 diabetes. It's the indication, right? If they take GLP-1 for just weight loss, maybe we don't want that. So having this as indication here is important as one of the inclusion criteria. So what is type 2 diabetes? Is it a drug? Is it a condition? Is it a demographic? Right, it's a condition. Right? So always make sure that when you choose here the criteria, you choose the correct domain. So in this case, we do want a condition occurrence. And so we want at least one occurrences of a condition of not any condition, right? I want type 2 diabetes. So then I will import another concept set that corresponds to type 2 diabetes. So to help me find my concept sets quicker, let me type in. Okay, so I find my type 2 diabetes concept set. I import it here. And where do I want these type 2 diabetes diagnosis to occur in a patient's record? It's probably better if it's prior to the treatment start date, right? So the patient that got a diagnosis of type 2 diabetes and later on they got put on a GLP-1 drug. That's often what we do. If you really say, well, if it's 30 days after it's okay, then I'm not gonna argue with you here, but usually these inclusion criteria are pre-treatment. So that means the event start date needs to be between, I think here I didn't put a time range for that. So we can say 365 days before and 0 days after the index start date. So the index start date always refers to the event in this cohort entry block, right? So this means, okay, now I want someone with a type 2 diabetes condition occurs within 365 days prior to their GLP-1 exposure. And so how to do a negative negation, having, let's say, no type 1 diabetes. How can we do that then? Right, so inclusion, exclusion, it's the same thing. So type 1 diabetes is another condition. So we want to add another condition block that what's important is with at least, you want to choose this to be, well, or at most, You can choose at most 0 or exactly 0. I think those two are equivalent. So right, want exactly 0 occurrence of type 1 diabetes. So import concept. Find. So I will find my type 1 concept set imported here. And then I say, right, type 1, we don't want a type 1 anywhere in the patient's any days prior to their GLP-1, then then it will be all days before and 0 days after index start date. So they cannot have type 1 diabetes anytime prior to their treatment start date. So this is how you put in, if you don't want some concept to happen in the cohort, this is where you change, is to, that's here. Are good so far? Any questions? All right, let's do one more. All right, so this is a GLP-1 cohort. Let's say we don't want anyone with prior exposure to DPP-4 inhibitors. Right, we want the GLP-1 is the first anti-diabetic drug they've ever received. So that means, okay, so no DPP-4 inhibitors. And this time, when I add the criteria, which domain should I choose from? Drug exposure. Excellent. Right, so because the DPP-4 is a drug. So I would say no DPP-4. So that means what do I need to put in here? Exactly 0, or this time let's say we do at most 0. Right? It's the same thing. And then import concept set.
While that's loading, is there a reason on principle that you would use drug exposure over drug era?
Good question. What do you think, Martijn?
Well, in this case, it doesn't really matter because we're basically excluding on basis of ingredient.
Right.
The only reason why I probably would prefer drug exposure is that there are actually quite a few sites that haven't populated the drug error table for reasons I don't know the meaning. But otherwise, it would be equivalent. Yeah. And you have to remember that if you have a drug error table, you don't see the individual prescription, which in this case doesn't matter.
Right. I guess if you wanted to exclude it based on some duration, if they used it for at least that number of days, then you would need the era.
Yeah.
Yeah. Okay, so this is how I create the no DPP-4 inhibitors criteria. And for the sake of time, I'm not going to do all the criteria, but I can show you one cohort that I created before the tutorial. I'll save it. All right, so I've created 3 cohorts, the GLP-1 target exposure cohort, DPP-4, the comparative exposure cohort, and also the outcome of interest acute MI. So if I click this, you see that it is, so we did this together. We add age. Here we did put this, the diabetes conditions here, which most of the time it shouldn't, it doesn't matter where you put the restriction criteria here or in the bottom, the new inclusion criteria section. I can see some slight edge cases where they can create a difference, but usually I think it doesn't matter. So this is no prior DPP-4 exposure, no prior exposure to SGLT2, so on and so forth. The only difference among these is just we use a different concept set. with prior metformin use. And this is, I copy exactly the cohort from Legend Type 2 Diabetes. So it has a lot more thoughtful design from the clinical team in terms of how often they think, how many metformin prior exposure patients should have in order for them to be eligible to be in this cohort. Similarly for insulin, how long they have to be insulin-free in order to enter the cohort. And these are things even beyond my knowledge that I would need to work with a clinician or a group of clinicians in order to really specify these correctly. And all the concept sets I used in creating this cohort are available here. So, and you can always look exactly what concept I include to define metformin, and do I include the descendants, and how many total concepts are there. And so that by leveraging the OMOP common data model and the hierarchy in the vocabulary, this makes the defining phenotyping much more rigorous and much easier. Imagine otherwise you would need to pick from these 8,000 variables to define a single concept, that metformin. Okay, so this is the target cohort. The comparator cohort is very similar to this. And that's usually what we do is, right, the inclusion-exclusion criteria should be similar for both your target and comparator cohorts. They should only differ by the cohort entry event, the exposure of a particular drug. So the outcome is cohorts is usually much simpler. The exposure cohort are the tricky ones, the more complicated ones. For example, in this case, the outcome is acute MI. So my cohort entry event for the outcome is always the condition that that of interest in the study, and I only need a diagnosis. It doesn't matter the the observation window, so on and so forth. That will be taken care of by the R code when we actually construct the study population. So you don't change anything. This is all I do is to import my acute MI concept set, which is this one. So there's a concept called acute myocardial infarction. And oftentimes, we include all descendants for a concept, except if this concept include, history of acute MI, then you want to exclude that. But those are, if you run into that, I'm sure there's many people in this community can help you to refine your concept sets. Okay, so I hope this is helpful to give you an idea of how to use Atlas to implement a lot of the inclusion-exclusion criteria for your exposure of interest, the outcome of interest, so on and so forth. Now, right, okay, so how can I've defined this all these cohorts in this web portal called Atlas. How can I actually use it in my R studio, right, in my Strategus implementation? So now we will, probably this is the time I'll switch to my own laptop. Thanks, Martijn. Okay, so if you have the study package downloaded, now you can open it by click the rproj icon. And if you run the rinf restore and you got that to finish, great. If not, don't worry. I will walk you through the files individually. So close all this. The first one that you will open is the one called download cohorts. Right, so you've spent all the time, define a cohort, create an atlas, now you want to put it down. There are manual ways to do it where you can, I should show that. There's an export tab in Atlas, and then you can click that and you can download as JSON or SQL. It used to be how I did it 7 years ago when I was a first-year PhD. I think at that time, maybe I wasn't aware of how I can download cohorts automatically with this. So this is the file. It's not long, 80 lines. So if you open it, all you need to change are the cohort IDs. For example, here, my GLP-1 cohort has a cohort ID from Atlas, that's this number, and this is for my DPP4, and this is for my AMI cohort. So I need to change 3 lines by typing 3 concept cohort IDs that corresponds to my cohort. Same for the 3 ones here. And you can name it, in this case, right, I named them this way. And if you want to renumber those cohorts, this is what you will do, right? So these concepts, in practice, I would just recommend doing a Control F, and let's say, right, if I want to change this cohort to something else, let's say I want to add another 0 at the end, and then just replace all, and that will change all the cohort in this file to your new cohort ID. I can renumber them into 1, 2, 3, so it'll be easier to say. And then the cohort generator, this is a OHDSI package. This is a package name called the cohort generator. And we oftentimes write code by, instead of using the library parentheses cohort generator, we actually type out the name of the packages, so it'll be easier for others to read and understand the code, which function comes from where. Anyway, so this will save the cohort definitions into our local folders called inst. I think it stands for instantiate, or maybe something else. And then for the negative control outcomes, so this is created as a concept set of, I'm just showing here as an example. So I create a concept set where I include 5 outcomes that I believe are negative controls in this study. And this is a concept ID from Atlas. So you will need to update this one. And then the rest should work out of the box. So I don't know if I have Wi-Fi here. Yeah. OK, so after you've modified this download cohorts R script, you will run it. And how do you know that this cohort have been successfully pulled down into your local folder? You will check this inst folder, and it will see that you should have these files and folders stored in your inst directory. It used to be, I think, 1 or 2 that I previously uploaded to the template, but if you see it looks like this, then you know that this cohort has been successfully pulled down. So for example, if I look up, I can show it here. So for example, the cohorts.csv now have my cohort IDs, their names from Atlas, or I think it's better to look at here. So the cohorts folder and 1.json. So this should correspond to our GLP-1 cohort, and all the information that we enter into Atlas, those inclusion criteria are now in this JSON file. Right, there's one criteria called patient should have type 2 diabetes, and this is block corresponds to that inclusion criteria. Okay.
So I don't see DSI list something.
DS.
You have it on your file, but I don't have
Oh,
DSI list. Should it be there?
yeah, so
They're on it, you,
we're almost there, almost there.
or it's next step.
Yeah, yeah, so, okay, we're at this step now, download cohorts, right? I show you, open this, download cohorts, our script, change the cohort IDs and the cohort IDs, or sometimes the concept set IDs that correspond to negative control outcomes. You run this file, and you should see an output that looks something like that. Okay, there's one file missing, and this could be I missed something in the workflow, but you need to create a cohort method target comparator list file. So in this case, for this example study, it's simple. We're just doing one comparison. And what you can do is to type in all this exactly as is into, open an Excel spreadsheet, put this in, and save it as a CSV file in inst. So I don't know if I need to. So it is a file that stores all the comparison that you want to test in your study. Like in this case, we're just comparing GLP-1 to DPP-4. But for example, in the Legend type 2 diabetes studies, we want to compare every drug class, anti-diabetic drug class, to every other class. So so that means 4 times 4, that's 16 different combination of target and comparator. Well, maybe half of that, right? Because if we switched mode, it's the same. But then we would have maybe 50 outcomes of interest. So that would be 16 times 50, and that will be a lot. So in that case, you probably want to write a for loop and script to generate this file. But if you just have one, I think, right, you can just type this into an Excel, right? Just like that. And save as, CM TC list. Make sure you have the exact same file name and store that under the inst folder. So save. Wow, it's annoying. And then inst. Yeah. So I had the one before. I will remove this. Confirm delete. View file. So this is the table that I had in that Excel file. And I also included a file that I didn't mention about called excluded covariate concepts. So this is the place where we, for example, we always exclude the drug concept. Right, for example, for a GLP-1 cohort, because we include all covariates up until the same day when the patient got that drug prescription. So if you include, so that means the drug concept IDs will also be included in your covariate set, and that will create a perfect correlation with your target or your target comparator group. So this is where we exclude that. Same for if you know there's instruments like a syringe, right, that should be excluded. This is a place where we add those concepts IDs that we want to exclude in this file. It looks a little bit messy this way, but if you open in Excel, it will look right. It's just a table with headers and some concept IDs. Okay, and so that's file number 1. Download cohorts, you run it, you get all these cohort information, the JSON files in here. Add this one file manually for now until I figure out the better way to do it automatically. Then the next file that you want to open is called Create Strategus Analysis Specification. There's 2 versions. It just, I think this one is a little bit older, but I think the community is moving towards using this one with TCIS. So I will show you this one. So in this Create Strategus Analysis Specification file, this is sort of where all the magic happens, or include all these cohort definitions, loaded them, and specify. So this is the file Tara showed you some screenshots. The first thing that you want to specify is this TCIS, the target comparator. I don't know what IS stands for. Indication. Oh, great. So in this case, my target ID is just 1, right? That's my GLP-1 cohort. I rename them to cohort 1, 2, 3. Comparator cohort is cohort number 2. I only want to include people with known gender, male or female. There's no age limits. And for my outcome cohort, that's cohort number ID 3. And in this case, the cohort has a clean window of basically all the time prior to exposure. Then you see this is the time at risk, where you specify do you want the risk window to start on day 1, or do you want to leave some grace period? And also for your cohort end date, is it the date when the event happened or the end of continuous observation, or do you want to add additional 30 days or something to the end of the cohort? So these are so in this case, right, with the at-risk time window starts the day after treatment start, and then it ends where the cohort exit event happens, or end of continuous observation. We don't add any buffering time to that. I comment out all the SCCS, the self-control case series code here in this template, but if you are, and sometimes we do run both the cohort method and SCCS, then you will uncomment all the codes that are related to SCCS. And then in a study protocol, usually we'll have a study start date and end date. For example, right, if I want to study start on December 1st, 2017 and ends on the end of 2024, this is where you put that information in. And this is just to accommodate different database. Sometimes dates are entered in different formats. Consider these settings for estimation. So this is specify some clean window for outcome look back. I think Tara mentioned this. Also, what propensity score matching do you want to do? Is a 1-to-1 or 1-to-many? So oftentimes we would do 1-to-1. So these things probably you don't need to change it in a study. And then you reach this line called do not modify. So follow the instructions and just don't modify it, and it will run. So these are codes so these are SCCS. So this is negative controls. So cohort generator module, this is a set of modules that now will take the cohorts those JSON files and generate them in the database. Cohort diagnostic module, this module includes all the specifications that will we will need to run the diagnostics. Characterization, cohort method module. So this is the module where we have the large scale propensity score and all the other good stuff that's in here. And pretty much the rest, you don't need to worry about it. Here is the kind of final step is we're gonna run these bunch of modules, including generate a cohort in the database. Maybe you want to do some characterization, right? You want to know the ratio men versus women, so on and so forth in the cohort. You want to run a large scale propensity score. And maybe you want to run SCCS. So, and you can comment out the ones that you don't want and just leave the ones that you want here. And that's how this template works. So at the end, we'll generate this file called, here I add a demo as a prefix, but analysis specification.json. And it will also be stored under the folder inst. So yeah, well, without internet, it's a bit tricky. So if once you finish this file, just run it, all of it. And the way that you know that you succeed is if you look under your inst folder and you see this demo analysis specification JSON. So if I open it, oh, wow, it's hard to read, but it's a big file with all the things that you need to run this analysis.
So we are well aware that editing an R file like this is very awkward. And so the next major version of Atlas will have a point-and-click interface for setting all these settings, but we first have to develop the analytics in R and make sure everything works before we actually build the interface. So we're now in an awkward situation where we believe this is the thing we should use, but it doesn't have a pretty interface yet. So apologies for that.
Yep. All right, and we're almost there. This is I think the hardest part. Once you have modify the analysis specification, then this is the last file that you need to open and change a little bit, which is called the Strategus code to run. So when you open this file, you basically need to change between line 20 to line 36. And that includes the first chunk are the name of your database. What's the database name, the schema, and in my case, this is where our OMOP EHR data is stored. The work database schema, this is the one that you need write access because so you can save tables. And this is one that I have for my lab. Our database is a Spark, which means it has some weird ways to generate temporary tables. So we need this additional line here to point the algorithm to a temporary schema where they can write some temporary tables in. And then you'll specify output location, your C drive, D drive, somewhere you want the output to be stored. And you can give a database name. It doesn't matter, just so the results folder will be created under this name. Min cell counts 5 is that we don't want to report anything that's less than 5 patients to protect privacy. And cohort table name, I named it a tutorial. And then you create a connection strings. This is to actually connect to the database. So database connector is an Odyssey package. And you need to specify what the type of database, the connection strings, user, and password. I'm showing here, but I'm sure nobody can remember that, that long string. I don't have internet. So there's an instruction here. We support 10 plus types of most common databases, Microsoft SQL, PostgreSQL. We happen to be using Spark at WashU. So this is how I connect to the database. And then that's the end of input. You don't need to modify anything else in this file below this line. And that will generate the, so once you're done, you run this entire code to run script, and that will perform all the analysis, diagnostics, just save those tables into your results folder. So what it looks like is, I think I have a slide. Yeah, so this was when I was doing it. So I ran it, and after it finished running, this is what I see. There's an execution summary. It tells me how long it takes each module to run, and for my cohort method, it was 11 minutes, so I'll total under half an hour. And this is my results, the structure of the results. So this is my template, right, where my GitHub repo, I have a results folder. This is my database name. If you have multiple databases, then you will have multiple folders there. I only have one, it's WashU. And Strategus output folder is the one that has all the outputs from your analysis. And that includes the covariate balance, diagnostics summary, and your cohort method results. That's CM_results. Yeah, that's the one that has the hazards ratio and confidence interval. We do not allow data partners to look at the results beforehand, but for training purposes, I'll show you this is the results that I got for this analysis. The top row is for the outcome of interest, the AMI. So we found hazards ratio of 0.8, a confidence interval of 0.4 to 1.5, and it's not significant, right, because it includes 1. And then the rest of the rows are the estimates for the negative control outcomes. So in this case, maybe one sort of works, the other NAs just means my database didn't have any patients with that negative control outcome. So in practice, we do choose negative control outcomes by knowledge and also the prevalence of concepts so that to avoid cases like this. But yeah, so that's pretty much it. We're at time.
Just a comment. So, you know, in this hour, which you can't memorize, but you can get the slides that can walk you through designing the study afterwards. Linying went through, I just want to emphasize what just happened because it's hard to, like, that was everything you need to do to run a study that gets published in BMJ, Lancet, or JAMA. Like, that's it. So yeah, you have to learn to program R, and you're not even programming in R. You're like looking at the name of the variable, and you're sticking in the thing that goes under that name of that variable. You're really just filling in this script. And what comes out of this thing, like there's a whole tutorial for 4 hours over there on characterization. So one thing that's going to come out of this thing that Linying just did is all the characterization of all the cohorts to tell you everything there is to know about the cohorts you put in to make sure they're okay. Now, in reality, you're going to spend, so that was like an hour of programming telling you while she did it. She could have done it faster. Your first one won't go in an hour, but your third one might only take an hour, and then it'll run for 3 days because it's actually doing some fairly complex stuff, or might run in an hour, or might run in 3 days, depends on what you ask it to do. You're going to get this characterization where it tells you everything about everything. Like, it's going to say for this cohort, it's going to say, like, for every other variable in the database, how's it related to the cohort you defined? So then you can go and look through, does this make sense? Well, I'm looking at angioedema. Well, what happened when they came to the clinic? Or what happened when they got this drug? And how is it related to that timing? And it's already pre-computed. Like, it did all that on the way through, the timing of everything in your database, those 60,000 variables against your cohort. So that's why it took an hour to do the thing, because it's actually doing all that. That's just before you even got to the analysis. And then it's going to run the analysis with all these diagnostics, with, you know, checking balance on 60,000 variables, checking equipoise, doing calibration according to these 70 negative controls. Like, that whole thing is there. And then you can do SCCS2 on top of it if you add it. And then it's doing a predictive model on top of that. I don't know why I don't need the predictive model. It's just in there in case you want it, and that's doing the prediction of the outcome. Like normally what would happen, I want a predictive model, so I'd comment out cohort method and SCCS and just do the predictive model, but you could leave it in there because it's actually pretty quick programming. Eventually the user interface will help, but like if you're willing to put in the time, like literally, that's why Anna Astropoulos was doing the data consult service where she was running studies like this, you know, in a day or two for people who had a question on the wards and give them the answer in a day or two for something that in the past, like 10 years ago, you spent a year doing some of these studies, programming and iterating. It'll take more than an hour because you're going to be doing some knowledge engineering in that and figuring out, oh, this cohort is not what I intended. But the thing is, the time you spend beyond the hour is not programming and analysis. It's doing the knowledge engineering, doing your human added value to the thing. So now you're being efficient, using your time to design the study and fix the study and not programming anymore. So it still seems like a big lift there, but like you're doing like the work of 20 programmers working in the background by just setting some of these parameters. So it really is a big change in how we can do research. And some of these papers that Cindy Kai that you'll hear about tomorrow at the plenary, you know, she just ran this network study on a zillion databases and published in JAMA Ophthalmology to counter the study that we didn't think was so good. Like it's just this rapid turnaround just changes things. Versus the other ones that came out quickly was like one database without good confounding control. Like another one database without good confounding control. And then we did ours, which is a gigantic network study with, I think, what is better confounding control, but more important, full diagnostics. We can argue whose confounding control is better, but we can show how well we did, whereas they don't even try to show how well they do. They just said, well, this is what we did. So that's the value of the Strategus package and the Odyssey stack to do these studies. So anyway, so I realize this is like step one of 10 steps to actually do your next JAMA or a Lancet or BMJ paper, but it's an important first step to get you guys there. So thank you for coming.